Hello there, and welcome to the Sleepy Facts channel. Tonight, we drift together into one of the softest and most comforting ideas in all of cosmology: the gentle, unhurried future of the universe. A future not defined by violence or catastrophe, but by a slow fading, a calm unwinding, a long exhale stretched across unimaginable eras of time. As you settle into your own quiet corner of the present moment, let your thoughts soften, let your breathing slow, and let the vastness of everything cradle you with its ancient, patient rhythm. For as long as humans have watched the night sky, we've wondered how all of this began. But there is an equally tender mystery in imagining how it all might end. Not the end of life as we know it, not the end of stars as they burn, but the far-off horizon where even time itself seems to loosen its grip. The end of the universe is not a cliff or a boundary. It is a horizon that recedes into infinity, a soft coastline slowly dissolving into mist. And the more we learn, the more we discover that this final chapter is less a moment of destruction and more a gentle transformation into stillness. As you listen, you might imagine the familiar glow of the night sky, the shimmering constellations, the Milky Way stretching like a soft river of light overhead. We see only a tiny fraction of what is truly out there. Beyond the edge of our eyes lies a tapestry of galaxies, clusters, and cosmic webs extending billions of light years in every direction. Yet even all of that brilliance is only temporary, a single bloom in a universe that is always changing. Stars rise, shine, and fade. Galaxies collide and drift apart. Black holes swirl like slow whirlpools in the vast ocean of space-time. Every moment has been part of a long story, and the ending of that story, when it eventually arrives, is written in the same patient ink. What scientists have discovered is both profound and strangely comforting. The universe's ending is not sudden. It is not violent. There is no single instant where everything shatters. Instead, it is a gradual cooling, a spreading, a drifting apart of all things. A long symphony whose final notes stretch across trillions upon trillions of years. A cosmic lullaby that fades into silence so slowly that even eternity seems unhurried. If you picture the universe as a great glowing lantern, its flame is nowhere near extinguished. It has only just begun to dim very slightly, so slowly that no creature, no planet, no civilization will ever feel it happen. The stars above you will continue to shine for billions of years more. And even after those stars fade, smaller, gentler ones, tiny red dwarfs glowing like embers, will carry the torch forward for trillions of years longer. The cosmos is still in its early morning. Its sunset is unimaginably far away, and even that sunset is not a drop into darkness, but a gradual drift into peace. The end of the universe is shaped not by one event, but by many eras that unfold like pages in a story written across forever. There will be a time when stars no longer form, because the great cosmic clouds will have been used up or stretched too thin to collapse under their own weight. There will be a time when galaxies, currently bound together by gravity, drift apart as space itself expands faster than light can cross it. There will be a time when the remnants of stars, white dwarfs, neutron stars, black holes, become the quiet monuments of a once luminous sky. And further still, an era when even black holes slowly evaporate in delicate whispers of radiation, fading into the background of a universe that has grown colder than words can describe. And yet, none of this is frightening. None of this is catastrophic. It is simply the universe returning to stillness. A candle that burns so long and so gently that its flame leaves no smoke and no ash, only a soft memory of warmth. Even now, as you sit or lie in your own quiet space, surrounded by the familiar rhythms of your breath and heartbeat, you are part of this cosmic story. Every atom in your body, was shaped by the universe's vast unfolding, from the hearts of ancient stars to the quiet spaces between galaxies. You carry within you the memory of the beginning. And someday, far beyond the reach of any imagination, the universe will carry the memory of us, held in the faintest traces of light, drifting through the calm. There is something deeply peaceful in knowing that the universe does not end with a sudden darkness or a final collapse. Instead, it stretches forward into a long, serene evening. A cooling of hot stars into warm embers, a softening of bright galaxies into quiet shadows, a transformation of matter into gentle radiation, spreading across a calm and endless sea of space. Nothing is lost abruptly. Everything transitions slowly, gracefully, like a tide going out. As you listen, you might imagine yourself floating through that far future, drifting through a sky where the stars have grown few, but each one glows with the deep, steady persistence of an ember in the dark. Imagine the vast openness, the quiet expanses, the deep calm of a universe that has all the time in the world. There is no urgency there, no struggle, just a slow unwinding of energy into stillness, a soothing release from the complexity of earlier ages. The end of the universe is not a threat. It is a lullaby, a reminder that everything, even the cosmos itself, finds rest. And in understanding that cosmic rest, we can sometimes find a little more rest within ourselves, knowing that the universe is not rushing toward anything, that it is simply breathing out into infinity, can help your own breath follow the same rhythm, slow, soft, and unhurried. So tonight, as we begin this journey through cosmic time, allow your thoughts to drift like stars through a widening sky. Allow your breath to fall into a quiet cadence, and allow the universe, ancient and gentle, to guide you deeper into rest. For in the story of the cosmos, even its ending is peaceful, even its final act is tranquil. And in that tranquil horizon, we may find a small, calm place of our own, one the universe is already quietly fading. From the moment the universe first expanded into being, an ancient rhythm began, a slow dispersing of heat, a gentle stretching of space, a cosmic breath that has continued uninterrupted for more than 13 billion years. Even now, as you listen, drifting gently within your own moment of time, the universe is continuing its quiet evolution. Nothing about it is sudden or rushed. Instead, the cosmos moves with the patience of eternity, changing so gradually that no creature, no star, no galaxy ever feels the shift. And yet the transition is everywhere. It is in the faint glow of cosmic background light that washes through the darkness. It is in the widening space between galaxies. It is in the cooling of once blazing regions that now carry only a soft whisper of heat. The universe is not collapsing or unraveling. It is simply fading, drifting into a calmer, quieter state with the passing of trillions of years. This fading began long before humanity looked upward and wondered about the stars, long before planets were born, long before even the first galaxies took shape. When the universe was young, it was hot and bright, filled with a density of light and matter we can scarcely imagine. But as it expanded, the heat spread out, the light stretched into longer wavelengths, and the early fire softened into a warm glow. That glow continued drifting outward, becoming cooler and quieter with each passing era. What remains today is the cosmic microwave background, a soft remnant of the universe's first light. It is a gentle haze of radiation that now chills at just a few degrees above absolute zero. It is not bright enough to illuminate anything. It is not hot enough to warm even the smallest speck of dust. It is simply the afterglow of creation, a faint reminder that the universe began bright and is slowly dimming. As galaxies stretch farther apart, their light grows fainter too. something subtle is happening across cosmic distances. The night sky, filled with stars and nebulas and soft rivers of starlight, is slowly losing its brilliance. Not in our lifetime, not in the lifetime of Earth, not even in the total span of all life that may ever exist here. Instead, this dimming unfolds over expanses of time that feel more like poetry than numbers. Over billions of years, galaxies drift apart, and the light they send toward one another must cross ever-widening oceans of space. As space expands, the light stretches, its color reddening, its energy diminishing until eventually it slips beyond visibility, becoming so gentle it can no longer be seen by any eye, biological or mechanical. In this way, the universe gradually quiets a little more with every passing epoch. Even the creation of stars is slowing down. In the early universe, galaxies teemed with vast clouds of hydrogen and helium, raw material for forming stars. These clouds collapsed under their own gravity, igniting billions of suns that filled the cosmos with fire. But those clouds are no longer as abundant as they once were. Much of the original gas has already been shaped into stars, and the stars have lived their lives and returned some of their material to space, but not in the same rich, dense form needed to spark endless cycles of new suns. Over time, the rate of star formation has fallen dramatically. New stars are still born, but the universe has moved out of its early youth where creation was constant and energetic. Now it is settling into a gentler phase, a long and peaceful adulthood. One day, far beyond any human future, the last generation of stars will ignite. These will be dim red dwarfs, stars so small and efficient that they will burn for trillions of years. They shine not like torches, but like embers, steady, faint, and enduring. They will outlive every other kind of star by immense margins. When the brighter stars extinguish themselves through supernovae or collapse, these tiny red lights will continue glowing quietly in the darkness. They are the caretakers of the far future, keepers of the last warm light in a universe slowly dimming. Their persistence ensures that even as the universe fades, it does so with grace, carrying its light far into ages beyond the reach of imagination. As galaxies drift apart and the cosmic expansion accelerates, the isolation between regions of space grows. Where once galaxies gathered in clusters and superclusters, sharing gravity and exchanging light, the future will see each cluster eventually standing alone in a vast emptiness. Gravity binds some galaxies together strongly enough that they will remain companions for eons. But beyond these small families, the universe will become a great expanse of dark, quiet space. This solitude is not harsh. It is simply a natural part of the universe's expansion, a slow drifting apart, like seeds carried by a gentle wind across an endless field. The fading of the universe is also seen in its temperature. As space stretches and matter becomes more dispersed, the heat of the cosmos continues to drop. Though the universe once burned at temperatures that could dissolve atoms, it now rests just above absolute zero, and it will fall even farther. The cosmic background radiation will fade until it becomes almost impossible to detect. Over countless trillions of years, the universe will cool to a temperature so low that motion itself slows nearly to stillness. Yet even this stillness is peaceful. It is not freezing in a hostile way, but cooling in the way a quiet night cools after a bright, warm day. Everything we see in the universe, stars, planets, nebulae, clusters of galaxies, is a temporary arrangement of matter and energy. Yet temporary does not mean fleeting. These structures endure for billions of years or trillions, enduring far longer than anything we could call familiar. But in the distant future, even these grand formations will evolve into simpler states. Stars will fade into white dwarfs, then slowly cool into black dwarfs, dark, dense remnants of suns that once lit worlds. Neutron stars will remain as silent monuments of collapsed matter. Black holes will govern the remaining architecture, slowly consuming what drifts near them. Each of these remnants represents a step in the universe's gentle exhale, a soft transition into quieter forms. As the universe continues this long fading, its future becomes more serene. There is no rush toward destruction, no sudden collapse waiting to catch the cosmos unaware. Everything unfolds in a long, slow rhythm. It is like watching a vast cosmic tide recede, pulling waves of light and heat back into the great stillness from which the universe first emerged. The end is not tomorrow or the next billion tomorrows. The end stretches so far beyond our timeline that it becomes something more like a story of eternity, a slow fade, a dimming of candles one by one, until only the softest afterglow remains. And in this fading, there is a remarkable tenderness. The universe is not ending because something has gone wrong. It is simply aging, moving into its later chapters. Just as stars are born, flourish, and fade, so too does the universe as a whole. And just as a quiet evening can feel peaceful after a long, vibrant day, the far future of the cosmos carries a profound calm, a stillness that reminds us that everything, no matter how vast, finds rest eventually. The universe is already on that trajectory, not with urgency, but with serenity. Even now, it is gently dimming, gently cooling, gently expanding. And in understanding this, we find an unexpected comfort. The cosmos is vast, ancient, and patient. Its fading is not a loss, but a slow transformation into quiet. A reminder that even the greatest story ever told ends not with a shout, but with a sigh, soft, gentle, and eternal. 2. Light itself will become rare. When we look up at the night sky, we see a world filled with light. Stars shimmer in quiet patterns. Galaxies glow from unimaginable distances. Nebulas stretch like watercolor clouds painted across the darkness. Even the places that seem empty are touched by the faintest traces of starlight scattered through the cosmos. We live in an age of brilliance, an era where the universe is still young enough to glow. But this radiance, as vast and boundless as it feels, is not permanent. In the long, slow future of the cosmos, light itself will become rare, stretching thinner and fainter until the universe enters an era of gentle dimness. Not darkness in a sudden or frightening sense, but a gradual softening, like the final minutes of dusk, where each color fades into deeper shades. It is a transformation so slow and so delicate that it feels more like the universe drifting into rest. Every beam of starlight that reaches us has been on a long journey. Light travels fast, faster than anything we know, but the distances between galaxies are enormous and growing larger. When the universe was young, distances were smaller, and light crossed from one region to another more easily. But expansion has been stretching space for billions of years, and as it continues, the fabric of the universe grows wider and thinner. As space stretches, it also stretches light. A photon that once vibrated in a bright, energetic frequency slowly becomes softened, elongated, redshifted. Its energy spreads out like a wave on a vast ocean. By the time it reaches distant galaxies, it carries only a faint whisper of its original brilliance. And with every passing era, this stretching becomes more pronounced, because the expansion of space is not slowing down, it is accelerating. This acceleration has profound consequences for the future of starlight. Galaxies that are now visible will eventually slip beyond a boundary called the cosmic horizon, a limit created by the speed of light and the expansion of space. Beyond that horizon, light cannot reach us, no matter how fast it travels, because the space between us expands faster than light can cross it. Imagine a distant lantern drifting away on an ocean whose waves constantly push it back. Although the lantern still glows, its light never arrives. It simply becomes unreachable. Over trillions of years, more and more galaxies will cross this horizon. Their light will fade from view, not because they have gone dark, but because the expanding universe hides them behind an unreachable distance. One by one, the heavens empty, until only the closest galaxy clusters remain visible to one another. Even within those clusters, light will change. The stars themselves will evolve. Brilliant, short-lived stars, blue-white giants that shine like cosmic beacons, will be the first to fade. They burn their fuel quickly, living only millions of years before collapsing or exploding. Those explosions once seeded the cosmos with elements, but in the far future, fewer and fewer new stars will form. The raw materials needed for star-birth dense clouds of hydrogen and helium have been steadily used up. The most luminous stars will disappear first, leaving behind a universe lit mostly by smaller, gentler stars. Red dwarfs, tiny points of warmth, will dominate the cosmic landscape. These stars burn so slowly and efficiently that they can glow for trillions of years, but even they are not eternal. In their final ages, red dwarfs will cool, their cores changing, their outer layers dimming. Eventually they will transform into white dwarfs, small, dense stars that shine only from leftover heat with no new fuel to burn. White dwarfs glow for incredibly long times, releasing their stored energy into the cold of space. But even this glow fades. Over trillions upon trillions of years, their surfaces cool and darken, turning them into black dwarfs, silent, cold remnants radiating no visible light. When the last red dwarfs become black dwarfs, the universe will lose its final shining embers. At that point, light from stars will no longer illuminate the cosmos. There will still be photons drifting through space, but they will come from sources far more subtle and gentle. The slow radiation of cooling matter, the faint whisper of particles decaying, and the rare collisions in the dark. Before that distant era arrives, the overall brightness of the universe will have been decreasing for an almost unimaginable length of time. Even now, if we were to observe the universe from its earliest moments to its farthest future, we would see it following a simple trajectory, from hot and radiant to warm and glowing, to cool and dim, and eventually to cold and barely luminous. The entire cosmos is undergoing a kind of cosmic dusk, but unlike dusk on Earth, where the sun sets in minutes, the universe's dusk unfolds over trillions of years. It is slow enough to feel like a natural exhale, a gentle conclusion to an age of brilliance. Yet the fading of light does not mean the fading of beauty. Even in deep cosmic time, the universe will carry quiet forms of light. Occasionally, the remnants of stars will collide. White dwarfs may merge, creating brief sparks of renewed brilliance, small supernovae that shine for a moment before fading. Neutron stars, too, may collide, releasing bursts of energy that flash across the darkness. And black holes, in their gradual evaporation through Hawking radiation, emit faint photons that ripple outward. These final sources of light are rare and soft, like the last embers in an ancient fire. They will not bring back the bright skies of the universe's youth, but they will add subtle points of radiance to the quiet expanses of the future. As time drifts on, even these faint glimmers will grow scarce. The cosmos will stretch so much that photons themselves, those tiny packets of light, will be redshifted into wavelengths so long, so stretched, that they will carry almost no energy. A photon that once belonged to the ultraviolet brilliance of a young star may, after trillions of years, stretch into a wavelength wider than galaxies. It will still exist, but its presence will be more conceptual than visible. It will be a reminder of the ancient universe, a ghost of brightness drifting through a cold, silent sea. But the rarity of light does not mean the universe becomes frightening or harsh. Instead, it becomes still. The quiet future of the cosmos is a place of profound calm, where energy is spread evenly and gently across space. Nothing erupts or collapses in dramatic fashion. Changes become subtle, patient, and almost meditative. Light, once the universe's most expressive storyteller, settles into a long and quiet outro, and there is beauty in that stillness too. A beauty rooted in the vastness of time and the tender way the universe unwinds. When we think of light becoming rare, it may seem like a loss, but in truth, it is simply a transition from one kind of universe to another. A universe of stars and galaxies gives way to a universe of faint radiation, drifting atoms, and long stillness. Each stage is natural. Each stage is the result of laws that have held true since the beginning. And each stage carries its own kind of grace. As you imagine this far-reaching future, you may find a strange sense of peace. Our own moment in cosmic history is bathed in light. We live among stars that illuminate the worlds around them, under a sky filled with ancient photons that have traveled unimaginable distances to reach us. To know that this era is temporary is not to fear its ending, but to appreciate its presence. The universe gives us this brilliant chapter, and then, in slow motion, it will turn the page. Light will become rare, but the universe will not mourn it. It will simply shift into a quieter mode of being, one where everything slows, cools, and settles. And in that quiet, the cosmos finds its rest, a rest so deep and gentle that the last traces of light drift like soft breaths through an endless night, carrying the memory of all the stars that ever shone. 3. The stars will finish their long work. From the moment the first stars ignited in the newborn universe, a slow and intricate story began to unfold, one written in light, heat, fusion, and time. Stars have always been the quiet engines of creation, turning simple atoms into the complex elements that shape planets, oceans, forests, and living beings. They are the forges where the universe learned to shine, the cosmic hearths around which galaxies gather, warm, and grow. And though they seem eternal to us, each star is a temporary lantern in a universe that measures its time not in millions or billions of years, but in epochs broader than human imagination. One day, far into the distant future, every star will finish its work. Not abruptly, not tragically, but in a gradual, graceful transition into stillness, as if the cosmos itself were exhaling after a long era of brilliance. To understand how stars complete their lives, it helps to remember how they began. The earliest stars were massive and wild, born from enormous clouds of primordial hydrogen and helium. They ignited with a fury that has not been seen since, shining millions of times brighter than our sun. But they lived quickly and died violently, seeding the universe with heavier elements: carbon, oxygen, nitrogen, iron, the very ingredients needed for life to take shape billions of years later. Those ancient giants burned through their fuel in only a few million years. Simple candle flames on a cosmic scale. They were short-lived sparks in a dark and expanding world, their brilliance brief but essential. As the universe aged, stars of more familiar kinds took their place. Medium stars like our sun, red dwarfs with their long-burning hearts, blue giants that flared in short flashes of intensity. Across galaxies, billions upon billions of stars lived out their quiet stories. Each one gathered itself into a sphere of light, balanced delicately between the inward pull of gravity and the outward push of nuclear fusion. This balance, the tug of collapse and the burst of creation, defined nearly everything we see in the night sky. Yet this balance is not eternal. Every star, no matter how stable, gradually changes as it consumes its fuel. Hydrogen, the simplest and most abundant element, is slowly transformed into helium in the star's core. This process releases energy, sustaining the star's glow. But eventually, the hydrogen runs low. The core contracts under its own weight, heating up, and fresh layers of hydrogen begin to fuse farther from the center. The star swells. Its color shifts. It becomes, depending on its mass, a red giant or a red supergiant, ballooning into a luminous, swollen phase that marks the beginning of its final acts. For smaller stars, like red dwarfs, this process is extraordinarily slow. Red dwarfs are the universe's most patient lanterns. They burn their fuel so efficiently that a single star can shine for trillions of years, hundreds of times longer than the current age of the universe. When humanity gazes at the cosmos today, most of the stars that dominate our view are relatively young, bright, and short-lived, compared to the humble red dwarfs that make up the majority of stars. These tiny, steady suns outlast all others. They flicker gently, their glow soft and faint, but despite their modest size, they are the longest-lasting sources of light the universe will ever know. When a red dwarf nears the end of its life, it does something remarkable. Unlike larger stars, which develop layered structures and complex fusion processes, red dwarfs burn through their hydrogen so slowly and thoroughly that they eventually become helium stars, maintaining their glow before gradually fading into white dwarfs without dramatic supernovas or explosive endings. Their transition is quiet, almost serene. Over trillions of years, they grow cooler and darker until they become black dwarfs, cold, dense remnants that no longer shine. These black dwarfs will be among the last macroscopic objects to exist in the universe. They represent the final breath of starlight. Medium-sized stars, like our Sun, live differently. After expanding into red giants, they shed their outer layers in delicate floating shells of gas, forming planetary nebulas, ethereal glowing clouds that shimmer like cosmic blossoms. At the center of each nebula remains a white dwarf, a small, bright ember of the star that once was. These white dwarfs shine for billions of years, gradually cooling, their light softening into deeper hues until they too fade into the silent state of black dwarfs. The planetary nebula disperses into space, adding its enriched materials to the galactic medium, where they may someday participate in the formation of future stars, planets, or even life. It is a cycle that continues, repeating again and again, until the conditions for new star formation dwindle. The most massive stars, instead, end their work in spectacular fashion. After burning through their hydrogen and helium, they fuse heavier and heavier elements until they reach iron, an element that cannot release energy through fusion. At that moment, the star's core collapses under its immense weight, triggering a supernova. This explosion is one of the most powerful events in the universe, bright enough to outshine entire galaxies for a brief time. The explosion scatters heavy elements into space, enriching the cosmos with the building blocks for planets and life. What remains of the star becomes either a neutron star, an object so dense that a teaspoon of its material weighs more than a mountain, or a black hole, a region of space-time so curved that not even light can escape its pull. Though these endings sound dramatic, on the scale of cosmic time, they are simply transitions, brief moments in a story that continues across aeons. But even the cycle of star, birth, and death does not last forever. As galaxies age and the supply of cold gas becomes scarce, star formation slows dramatically. Over trillions of years, fewer new stars will form. Existing stars will reach the ends of their lives without replacements to take their place. Eventually, the universe will enter an era where the last generation of stars is born. These will be small, faint red dwarfs, celestial candles that take trillions of years to flicker out. When the final red dwarf ignites, the era of starlight will reach its peak, and then slowly, begin to decline. Imagine gazing at the night sky in that distant future. The bright stars would be gone, replaced by a sparse scattering of dim, red points. The Milky Way, if it still exists in a recognizable form, would appear far darker. Nebulas would be rare or non-existent. The great star-forming regions, once vibrant clouds where new suns and planets emerged, would have thinned to almost nothing. The universe would seem quieter, more spacious, more empty. But in that emptiness, a gentle kind of beauty would remain. The stars still shining would be calm, steady, and enduring, each one a tiny flame burning against the long cosmic night. And when the last star finally finishes its work, when the last red dwarf flickers into a white dwarf and then fades into a black dwarf, the universe will not mourn the light it once held. Instead, it will settle into a new state, a peaceful darkness where energy becomes scarce and motion slows. The elements created by countless generations of stars will remain dispersed throughout the cosmos, silent memories of the luminous ages. The universe will have completed one of its grand tasks: the creation, evolution, and eventual fading of stars. This far future is not a tragedy. It is the natural conclusion to a long, radiant chapter in cosmic history. Stars are born, they shine, they transform, and they finish their work. And in acknowledging this, we find ourselves held by a quiet truth. Even the brightest things in the universe eventually rest. The stars do not resist their endings. They simply reach them, gracefully, after lifetimes so long we can scarcely comprehend them. In the soft glow of the present, we live in a universe still rich with starlight. This is our moment within the cosmic story, the warm, golden age when stars still fill the sky, when galaxies still shimmer from horizon to horizon. But in the distant future, when the stars have finished their long work, the universe will drift into calm, into stillness, into peace. And just as night follows day, this transition will be gentle, patient, and beautifully serene. 4 galaxies drift into the distance. When we look at the night sky from Earth, or from any planet circling any star in any corner of the cosmos, we see a universe stitched together by immense structures. Clusters of galaxies arc across the darkness like threads of light. The Milky Way glows overhead as a river of stars, woven from the gathered brilliance of hundreds of billions of suns. Even the darkest parts of the sky hold faint galaxies, soft smudges of ancient light that have traveled for millions or billions of years. Everything seems connected. Everything seems close enough to form a visible tapestry. Yet, the cosmos is not fixed. What appears to be a still painting is, in reality, a vast choreography of motion. And one of the quietest, most far-reaching changes happening right now, every second of every day, is the gentle drifting apart of galaxies, a motion that will continue into the deep future until the universe feels more like an endless ocean with islands scattered far beyond one another's reach. The story begins with expansion. Since the first moments after the Big Bang, space has been stretching, not like an explosion sending debris outward, but like the fabric of reality gradually unfolding. Galaxies are not flying through space so much as space itself is growing between them. Imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from every other dot, even though none of them are actually traveling across the surface in the usual sense. The same quiet expansion is happening throughout the universe, and has been happening from the very beginning. For billions of years, this expansion was steady, slow, a gentle widening of cosmic distances. But something unusual occurred around 6 billion years ago. The expansion began to accelerate. Something, perhaps dark energy, a mysterious and invisible force, began pushing galaxies apart faster and faster. Even now, galaxies drift away from each other at speeds we can scarcely imagine. The farther away a galaxy is, the faster it recedes, as though the universe is stretching most strongly where it is the widest. We can see this in the redshift of light, the way the wavelength of light lengthens as galaxies move away, making their color shift toward the red end of the spectrum. This stretching of light is the universe's quiet way of telling us what is happening across the vastness of space. Each beam of starlight carries the story of its journey, elongated by distance, softened by time, fading into a gentle whisper of its original brilliance. As trillions of years pass, this drift becomes profound. Galaxies that are already far away will slip beyond what is known as the observable horizon, the boundary beyond which light can no longer reach us. This horizon is not a wall or a barrier, but a natural limit created by the expansion of space itself. Light from galaxies beyond that boundary tries to cross the distance between us, but the space in between expands faster than the light can travel. Eventually, those galaxies simply vanish from view, not because they cease to exist, but because their light will never arrive. It is as if they dissolve into the darkness, becoming memories of a time when the universe was more compact. In truth, they continue their own journeys elsewhere, drifting farther and farther into an ever-expanding ocean of space-time. The Milky Way, our home galaxy, is not immune to this cosmic drift, but it belongs to a special group, a small cluster of galaxies held together by gravity. These local galaxies, including the Andromeda Galaxy and a sprinkling of smaller companions, are close enough that gravity can resist the expansion of the universe. Over billions of years, these galaxies will drift toward one another, eventually merging to form a larger, elliptical galaxy, sometimes called Milkdromeda. Everything within this gravitational family will remain bound together, sharing the same cosmic fate. But beyond this cluster, other galaxies will fade from view, one by one, until the night sky contains only the stars of our merged home galaxy and the faint glow of a few nearby structures. Everything else will have drifted beyond reach. Imagine standing beneath a sky in that far future. Instead of seeing billions of galaxies scattered across the cosmos, you might see only one, your own, a single glowing structure, stretching in a soft arc across the darkness. The rest of the universe, once vibrant with distant lights, will appear empty. This emptiness is not hostile. It is simply the natural result of expansion, stretching space so wide that galaxies grow isolated. The cosmic web, the intricate network of filaments that once connected clusters of galaxies like the branches of an intergalactic tree, will appear to unravel. What remains are quiet islands of gravity, floating in a sea that expands forever. This drifting apart will continue at an accelerating pace. In the distant reaches of the future, the expansion will grow so strong that even the faintest photons traveling across space will be stretched into wavelengths longer than entire galaxies. Their energy will become almost non-existent. The universe will transition from a cosmos filled with light and structure to one filled with gentle radiation, thinly spread across expanding space. The brightness of the early universe will feel like a distant dream, its echoes preserved only in the most ancient backgrounds of radiation. Yet this future is not bleak. The drifting apart of galaxies does not represent a loss, but a transformation. In the early universe, everything was packed tightly together, hot and nearly uniform. Over time, matter condensed into stars and galaxies, forming structures full of complexity and beauty. The future, where galaxies drift apart, is simply another phase of this long evolution, a gradual softening, a quiet expansion into spacious stillness. What remains in each gravitational pocket is not chaos, but stability. Stars will continue to orbit the centers of their galaxies. Planets, if they still exist, will continue to trace their paths. Life, if it endures, will adapt to a sky with fewer distant lights. The universe becomes more isolated, but also more peaceful. As galaxies drift apart, a subtle poetry emerges. The cosmos spreads itself thin like a canvas being stretched over an ever larger frame. The patterns remain, but they grow softer. The colors fade. The shapes become less distinct. A painter might call this blending or dilution. A poet might call it quietude. The universe simply calls it expansion. There is something deeply calming about imagining this drift. We often think of movement as fast, dramatic, or chaotic. But cosmic movement is slow, patient, and extraordinarily smooth. Galaxies drift like feathers on a cosmic breeze. Their paths are guided not by chaos, but by the steady unfolding of space-time itself. We are part of this motion, carried along effortlessly, without resistance, like passengers floating on an invisible current. And in that motion, there is an immense serenity. Eventually, the distances between gravitationally bound clusters will grow so vast that even the concept of between becomes difficult to grasp. Space will seem like an endless field of darkness, punctuated only occasionally by small pockets of stars. And yet, for those who inhabit those future pockets, their immediate world will still feel full and vibrant. Perspective, as always, shapes experience. Just as ancient humans once believed the sky ended at the edge of their village, future beings may look up and see only their local cluster, believing it to be the entirety of the cosmos. The broader universe will have drifted beyond their horizon of knowledge, leaving behind a simpler, quieter sky. In this distant future, galaxies drift into the distance, not with violence, but with gentleness. Their separation is not a tearing, but a stretching, not a loss, but an expansion of the cosmic stage. And as they drift, they write the story of a universe moving from brightness into stillness, from closeness into quiet solitude. It is a slow unfurling, a cosmic sigh that lasts for eternity. And in that sigh, we find a peaceful reminder. Everything moves, everything changes, and even the grandest structures in existence drift softly, patiently, into the endless night. 5. The universe becomes a place of lonely islands. As the universe continues its slow expansion, a quiet transformation begins to unfold. One so gradual that no star, no galaxy, no living being will ever sense the moment when it begins or ends. It is a change written not in sudden events, but in the gentle accumulation of distance. What was once a cosmos filled with interconnected structures, a vast web of galaxies shimmering like dew on a cosmic web, slowly begins to unravel, not violently, not abruptly, but like threads pulled apart by the steady hands of time and space. In this far future, the universe becomes a place of lonely islands, isolated clusters of galaxies, drifting farther and farther away from one another, across an ever-widening sea of darkness. To imagine this future, picture the universe as it appears now. Galaxies are not scattered randomly, but arranged in vast filaments, long strands of matter weaving through enormous voids that span millions of light-years. These filaments crisscross the cosmos, connecting clusters of galaxies like the branches of a great cosmic tree. Within these branches, gravity binds galaxies together, guiding their motions, shaping their fates. But between the branches lie gulfs of emptiness, regions so sparse that a single particle of matter might wander for hundreds of miles before encountering another. Even now, this structure shapes everything about the universe. It dictates how galaxies grow, how matter clumps, how stars form. Yet, as the universe expands, this cosmic web begins to stretch. The filaments thin, the clusters drift, the voids widen. At first, nothing seems different. Stars still twinkle in the night sky. Galaxies remain visible in telescopes. The cosmic web, though stretching, still holds its shape. But over billions of years, expansion accumulates. Imagine drawing 2 points on a piece of taffy, then gently stretching the taffy a little more each day. At first, the points seem unchanged, but given enough time, the distance between them doubles, triples, then becomes so great that they might as well be on different worlds. This is how the universe behaves. Space expands, not all at once, but continuously. Every second, every moment, the distance between galaxies increases, even if only by the tiniest fraction. Over eras of time so vast they defy normal comprehension, this steady stretching reshapes the cosmic landscape entirely. The first sign of the coming isolation is the disappearance of the most distant galaxies from view. As space expands, their light stretches into longer wavelengths, becoming redder and fainter, until, eventually, it slips beyond the range of any detector. They become invisible not because they no longer exist, but because the universe's expansion outpaces their light. One by one, these distant galaxies vanish from sight, slipping beyond the horizon of the observable universe. This boundary is not a wall or a barrier, but a horizon created by the speed of light and the expansion of space. Beyond it, events unfold that will never reach us, no matter how powerful our telescopes or how long we wait. Eventually, only the galaxies within our local gravitational cluster will remain visible. This cluster, often called the local group, includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and a collection of smaller companions. Gravity binds these galaxies together strongly enough to resist the expansion of space. Over billions of years, they will drift toward one another, merge, and settle into a single, enormous, elliptical galaxy, an island of matter in an emptying universe. But beyond this merged structure, no new galaxies will appear. No new light will cross the vast gulf of expanding space. The local group will be alone, floating through a cosmic ocean that grows more silent with every passing era. For future observers, if observers exist at all, the night sky in this distant future will look vastly different. They may gaze upward and see only the stars of their own galaxy. No distant galaxies will adorn the horizon. No soft glow from clusters millions of light years away. No faint smudges of starlight traveling across the darkness. Their entire concept of the universe will shrink to this single island of stars, the only visible structure remaining. They may conclude, reasonably and understandably, that the cosmos contains only one galaxy. They may never know that countless others once shared the sky, glowing brightly in a universe filled with light and connection. The vast web that once wove galaxies together will become invisible, not through destruction, but through distance. As expansion continues, the universe enters an era of deep solitude. The islands of matter clusters held together by gravity drift through a void that becomes increasingly empty. The space between these clusters grows so large that crossing it, even at the speed of light, would take longer than the current age of the universe multiplied trillions of times. It is an ocean without shores, a sea without tides, a night without dawn. And yet, even within this isolation, there is a quiet beauty. The galaxies within each island continue their slow dances. Stars orbit one another. Planets trace their paths. Solar systems evolve in their own self-contained worlds. Life, if it survives, may adapt to the changing cosmos, finding new ways to endure, even as the larger universe fades from view. In this distant era, the isolation of galaxy clusters does more than reshape the night sky. It alters the flow of time, the movement of matter, the rhythms of cosmic energy. With fewer interactions between galaxies, collisions become rare. Star formation slows even further. The gravitational tides that once rippled across regions of space settle into calmness. Over trillions of years, the galaxies within each cluster will use up their remaining gas, transform their stars into remnants, and settle into long-lasting structures that change only on the most extended scales. These clusters become cosmic sanctuaries, preserved against the vast and growing emptiness. Eventually, even interactions within these isolated islands begin to fade. The galaxies inside each cluster slowly merge, drawn together by gravity until they form a single, enormous structure, an elliptical galaxy containing the remnants of countless earlier generations. The stars within this merged galaxy age together. The bright, youthful stars gradually give way to older, cooler ones. Stellar nurseries disappear, nebulas dissipate, star formation ceases. The galaxy becomes a quiet sphere of aging light, glowing serenely in a night that no longer holds any companions. As the universe continues to expand, even the faint radiation left over from earlier epochs stretches thinner and cooler. What once bathed the universe in a gentle microwave glow becomes softer still. In time, even the most energetic particles become rare. The cosmos cools toward near absolute zero, not abruptly, but slowly, like a warm ember fading over countless ages. The lonely islands drift through this cold, silent ocean, each one carrying the last traces of starlight, the last remnants of cosmic structure. It may seem like a stark future, but it is not a sad one. There is a peacefulness to this vision, a sense of the universe settling into its final form. The era of interconnected galaxies, rich with light and motion, is temporary. The era of solitary islands, drifting through a calm and infinite sea, is its natural continuation. The universe is not breaking apart, it is spreading out, relaxing into an ever-widening expanse. And just as night follows day, this transformation carries its own kind of grace. The galaxies, once woven together like threads of a great cosmic tapestry, will become gentle lanterns drifting on a dark horizon. The universe may become a place of lonely islands, but in that solitude lies a profound stillness, the quiet rest at the end of a long, luminous journey. 6 black dwarfs, the quiet remains of stars. When we look up into the night sky, we see stars shining with a brightness that feels eternal. Their light seems steady, unwavering, and older than memory itself. The truth is both more delicate and more extraordinary. Every star, no matter how enduring, carries within it a slow and quiet story of transformation. And one day, long after its shining days have passed, a star becomes something far softer, far dimmer, and far quieter than we can currently witness. It becomes a black dwarf, an object so still, so cold, and so patient that it represents one of the final forms of matter in the luminous universe. These black dwarfs do not yet exist in the cosmos today, for the universe is still too young for any star to have cooled enough to become one. But in the deep future, they will fill the quiet corners of space, silent monuments to once brilliant suns. To understand black dwarfs, imagine tracing the life of a star from its beginning. Most stars, including our Sun, are born from vast clouds of hydrogen and helium cosmic nurseries, where gravity pulls gas inward until it becomes dense and hot enough to ignite nuclear fusion. Once this process begins, the star stabilizes. It glows with a steady light as hydrogen in its core is fused into helium. This balance can last billions of years, depending on the star's mass. Our Sun, for instance, has been shining for nearly 5 billion years and will continue to shine for several billion more. But even stars with such longevity eventually exhaust their hydrogen fuel. When a star like the Sun runs low on hydrogen, it swells into a red giant, shedding its outer layers and exposing its hot core. What remains after this shedding is a white dwarf, an extremely dense, Earth-sized object, made mostly of carbon and oxygen. A white dwarf shines not because it has a source of fuel, but because it is still hot, glowing with the residual heat of its past. Imagine a piece of metal heated in a furnace. If left alone, the metal slowly cools, its glow fading from bright white to dull red and eventually to black. A white dwarf undergoes a similar journey, but over an incomprehensibly longer time. White dwarfs are among the longest-lasting objects in the universe. They begin their lives with temperatures of millions of degrees and slowly radiate away their heat. The process is so slow that even the oldest white dwarfs we have observed, those formed not long after the first stars died, are still glowing faintly. The universe simply hasn't existed long enough for any white dwarf to cool completely. But eventually, after trillions, quadrillions, or perhaps even quintillions of years, a white dwarf's glow will fade entirely. Its temperature will drop close to absolute zero. Its light will vanish. And what remains is a black dwarf, a stellar remnant as quiet and cold as the space around it. A black dwarf is the final stage of a star that died gently. Unlike supernova remnants or neutron stars, which have dramatic origins, black dwarfs arise through softening and cooling. They are stars that have surrendered their last warmth to the universe. They are the husks of suns that once lit worlds, now resting in the deep calm of cosmic time. Their surfaces, once blisteringly hot, become cool enough to be touched without burning, though they exist in places where no hand will ever reach. Their atoms settle into stillness. Their glow is gone. Yet their structure remains intact, preserved like a memory. In the distant future, when the universe has aged beyond the spans we can fathom, black dwarfs will become one of the most common objects in existence. The bright stars that fill our skies will be rare or non-existent. The galaxies, once crowded with luminous suns, will appear as vast fields of darkness, dotted with occasional faint remnants. These remnants, black dwarfs, scattered throughout the lonely islands of galaxy clusters, will be the quiet keepers of what once was. It is difficult for us to imagine this world because no black dwarfs exist yet. Every white dwarf in the cosmos is still glowing, still cooling, still on its long descent into darkness. But astrophysicists calculate that the transformation from white dwarf to black dwarf will take longer than the current age of the universe, by a factor of thousands or millions. 1 trillion years, the blink of an eye compared to what is needed, will barely begin the cooling process. Only when the universe is older than nearly all its stars, older by orders of magnitude, will black dwarfs begin to appear. When they do, the universe will be vastly different from the universe we know. The expansion will have stretched galaxies apart into immense solitude. Star formation will have long ceased. Most stars will have died. Black holes will dominate the centers of galaxies, slowly evaporating through Hawking radiation, their voices fading into the background. And in the outer reaches of each galaxy remnant, black dwarfs will drift quietly, each one a frozen relic of a once shining star. They will orbit in darkened space, moving slowly through the remnants of a galaxy that no longer glows. Yet even in their silence, black dwarfs possess a quiet beauty. They represent endurance on a scale that defies human comprehension. They embody the persistence of matter, the way the universe holds on to its creations long after their brightest moments have faded. They are reminders that even after the fire of a star is gone, something remains, something steady, something enduring. They are the embers of the cosmos, cooled beyond glow, but still present. In the unimaginably distant future, some black dwarfs may experience something extraordinarily rare and subtle fusion triggered by quantum tunneling. Over timescales so immense they dwarf any other process we know, the atoms inside a black dwarf may rearrange themselves. Carbon atoms could fuse into heavier elements, releasing energy in brief, soft flashes. These events would be the last moments of stellar activity in the universe, tiny flickers in an otherwise darkened cosmos. They would not illuminate galaxies or bring warmth to the surrounding void, but they would represent the final breaths of stars, the last echoes of thermonuclear fire in a universe that has grown cold and still. After these final flashes, the black dwarfs will experience their own kind of quiet death. Their matter will become inert, their atoms locked into place. They will join the other remnants of a universe that has reached the end of its luminous era. And yet, even this ending is not dramatic. It is gentle, as if the universe is easing itself into rest after a long, brilliant lifetime. Thinking of black dwarfs invites us to reflect on the timescales of the universe. We measure our lives in decades, our histories in centuries, our civilizations in brief chapters of a few thousand years. Stars measure their lives in billions of years. But black dwarfs ask us to stretch our imaginations further, to consider what happens not after billions, but trillions, quadrillions, and more. They show us that the universe's patience extends far beyond what we can feel or touch. And in that patience lies a remarkable serenity. In the far future, when black dwarfs drift silently through space, the universe will have become a quiet, dark place. But it will not be empty of meaning. Those dark remnants carry the history of light. They hold the memory of stars that once shone, of planets that once orbited, of galaxies that once glimmered with life and motion. They are the final chapters of a cosmic story that began with blazing brightness and will end in peaceful quiet. And in their cold, dark forms, they offer a reminder that even when brilliance fades, something steady remains, a calm presence, resting in the vastness of time. In this way, black dwarfs are not symbols of loss, but symbols of endurance. They show us that even after the universe has dimmed, there will still be remnants of its earliest fire, resting quietly in the dark. And through them, the cosmos continues to speak softly across eternity, whispering the final verses of its long and gentle song. 7. The gentle reign of gravity. From the earliest moments after the universe's birth, gravity has been the quiet architect guiding everything that followed. It is the soft, persistent pull that gathers dust into planets, planets into solar systems, and solar systems into galaxies. It shapes the arcs of comets, the spirals of galaxies, and the slow drifting motion of stars through the deep. Even now, as you sit or lie in your own small corner of space, gravity holds you to the earth with a tenderness so constant you rarely think about it. It has no voice, no color, no sound. And yet, it is the most patient sculptor the universe has ever known. In the far future, long after the last bright stars have faded and the great clusters of galaxies have drifted into isolation, gravity will continue its quiet reign, shaping the universe in softer, subtler ways. To understand its role in the universe's long future, imagine stepping back from the cosmos we see today. Galaxies still swirl with stars, clusters still shimmer with billions of suns. There are collisions, mergers, and bursts of light, but these moments of brilliance happen against a backdrop of gravitational structure that has been stable for billions of years. Even as the universe expands and galaxies recede beyond one another, gravity maintains its influence on smaller scales. It holds galaxy clusters together. It binds galaxies into single entities. It guides the orbits of stars around invisible centers. And as the universe cools and dims, gravity becomes the final organizing force, remaining long after light fades and matter grows still. In the distant future, after galaxies have stopped forming new stars, the structures shaped by gravity will remain. Within each isolated cluster of galaxies, gravity will continue to pull stars toward one another. Over trillions of years, gravitational interactions cause stars to drift into new orbits. Some stars get flung out into intergalactic space, drifting alone through the dark. Others spiral inward, moving closer to the galactic center. These motions are incredibly slow, a gentle dance stretched across eras. But given enough time, everything within a galaxy drifts toward a new and quieter equilibrium. One of the most profound ways gravity shapes the long future involves the remnants of stars. As luminous suns fade into white dwarfs, neutron stars, or black holes, gravity remains as the force that governs their motions. White dwarfs orbit the galactic center with the same understated grace as their parent stars once did. Neutron stars, dense and silent, drift through the dark as faint echoes of once massive suns. Black holes anchor themselves in the deep, invisible wells of gravity they carve into space-time. These remnants interact with one another through gravitational encounters that continue long after light has grown scarce. As galaxies evolve, gravity slowly gathers many of these remnants toward the center. This process, called dynamical friction, acts like a cosmic drag. The collective gravity of all the stars and dark matter slows the motion of massive objects, causing them to sink inward. Over trillions of years, this process leads to the gradual migration of neutron stars and stellar mass black holes toward the galactic core. There, over unimaginable stretches of time, they may collide or merge, forming larger and more massive black holes. At the heart of nearly every galaxy lies a supermassive black hole. In our own Milky Way, the central black hole holds millions of times the mass of the Sun. In larger galaxies, these central black holes can weigh billions of solar masses. Their gravitational influence extends far beyond their event horizons. They shape the orbits of nearby stars, determine the structure of the galactic core, and influence how matter settles within the inner regions. As time passes and galaxies merge, their central black holes merge too. In the far future, each isolated cluster may eventually host a central black hole so massive that it dominates the gravitational landscape of its entire region. When galaxies within a cluster merge, gravity orchestrates the entire process. It is a slow choreography, a long, swirling movement that can take billions of years. Stars rarely collide during these mergers because they are spaced so widely apart. Instead, they pass like ghosts through one another's paths, but their orbits change, shaped by the gravitational tug of the merging galaxies. Gas clouds, if any remain, are compressed, triggering brief bursts of star formation that illuminate the merging galaxies for a time. Eventually, the chaotic motions settle. The new galaxy becomes a vast, smooth, elliptical shape rounder, larger and quieter than the spirals from which it formed. As star formation ceases, gravity remains the dominant force within these elliptical giants. Without the bright, messy dynamism of young stars and swirling gas, the internal motions of galaxies become calmer. Stars trace long, stable orbits. The interstellar medium becomes sparse and cold. Gravity guides everything into a state of slow, drifting equilibrium. Over even longer timescales, the remaining stars gradually interact with one another through tiny gravitational nudges. These interactions are too small to feel in any human sense, but over trillions of years, they accumulate. Some stars are gently nudged outward, leaving the galaxy entirely. Others are drawn inward, falling toward the central black hole. In this distant era, the universe is dominated by structures shaped entirely by gravity. Galaxies have turned into quiet spheres of stellar remnants, drifting silently through space. Black holes, once formed in violent supernovas, grow through mergers and through the slow accretion of matter that wanders too close. Gravity remains the cosmic caretaker, guiding matter into the places where it settles, drawing the universe into a state of calm and quiet order. Even the large-scale structure of the universe, which once held vast networks of filaments and clusters, is shaped by gravity's past influence. Though the expansion of space eventually pulls clusters apart beyond one another's horizons, the imprints of gravitational formation remain in each isolated island. The shapes and distributions of stars, the densities of dark matter halos, the patterns of orbits all reflect the long reign of gravity during the universe's luminous ages. Eventually, the universe enters an era where luminous matter becomes rare. Stars fade into black dwarfs. Neutron stars cool. Even black holes, though incredibly stable, slowly evaporate over unimaginable timescales through Hawking radiation. Gravity governs these processes too, not through sudden force, but by shaping the environments in which these objects evolve. The slow evaporation of black holes is governed by quantum physics, but their ability to remain dominant for so long is rooted in the extraordinary strength of their gravitational pull. Though they fade at the end, they persist long enough to outlast nearly every other structure in the universe. If we project forward far beyond the lifespan of galaxies into timescales measured in powers of 10 that stretch across the imagination, we find that gravity becomes the final force shaping matter. Particles drift through ever-expanding space. Black holes evaporate. Remnants move farther apart. But gravity's influence persists in the very curvature of space-time, the invisible imprint left by every mass that ever existed. Even when the universe has become dark, cold, and almost entirely empty, the geometry of space still carries the signature of gravity's ancient work. There is something profoundly peaceful in this vision. Gravity does not shout. It does not blaze like a supernova or flash like a gamma-ray burst. Instead, it whispers, it guides, it shapes with infinite patience. In the far future, as the universe drifts into silence, gravity becomes the final companion of matter, the last gentle sculptor in a cosmos that has grown calm. And as we imagine this future, a universe filled with quiet orbits, dark remnants, and slowly drifting particles, we find ourselves held in a sense of cosmic stillness. The long reign of gravity is not a story of collapse or destruction. It is a story of order, of persistence, of gentle guidance across aeons. It is the slow, steady heartbeat of the cosmos, continuing long after the last star has gone quiet. 8. The era of black holes begins. As the universe matures beyond the age of starlight, a profound transition unfolds, quiet, patient, and shaped by the long, slow rhythm of cosmic time. The brilliant era of fusion, where stars illuminated the darkness and galaxies shimmered with rivers of light, eventually gives way to an era governed by remnants. White dwarfs cool. Neutron stars sit in silent density. Black dwarfs wait in the dark. And in this shifting landscape, one type of object begins to rise to prominence. Not through violence or sudden change, but through endurance. Black holes, those deep, silent wells in space-time, become the dominant structures in the cosmos. What was once rare and dramatic becomes, in the far future, the quiet anchor of entire galaxies. This marks the beginning of the era of black holes, a long chapter where gravity, darkness, and time weave the universe into a new kind of calm. To imagine this era, picture the universe long after its brightest days have passed. The stars have mostly faded. Only a scattering of red dwarfs remain, glowing faintly like embers in the night. Their light, though steady, is not enough to illuminate galaxies the way massive stars once did. The luminous Milky Way we know becomes dimmer and quieter, its spiral arms losing their definition. As these last stars drift toward the ends of their fuel, they join the others in becoming remnants, white dwarfs, neutron stars, or black holes. Each galaxy, once vibrant with ongoing formation, settles into an older, more subdued structure, composed almost entirely of remnants. Among these remnants, black holes stand apart, not because they remain bright, but because they endure. Already today, black holes occupy the centers of most galaxies. The Milky Way has one, a supermassive black hole with millions of solar masses. Other galaxies host even larger ones, weighing billions of times more than the Sun. These black holes were forged through mergers, accretion, and the collapse of immense stars. But in the luminous universe we know, their influence is balanced by the presence of stars and gas clouds. They pull, but the galaxy around them shines. In the far future, when the stars have faded, their gravitational presence becomes far more significant. They are the anchors around which the remaining matter orbits, the deep wells at the centers of the cosmic islands left behind by expansion. As galaxies merge over trillions of years, their central black holes merge as well. These mergers are slow, graceful spirals inward, where two enormous objects dance closer and closer until they coalesce into one. Each merger releases ripples in the fabric of space-time gravitational waves that echo silently across the darkness. These waves carry away energy, allowing the black holes to draw nearer to one another until they become a single, larger whole. Over cosmic time, this process repeats within each gravitationally bound region. The supermassive black hole at the heart of each merged galaxy grows larger and heavier, becoming the dominant object not only in mass but in influence. Eventually, each galaxy, or each merged cluster, will host a single central black hole that contains a staggering portion of all the mass that once made up stars, planets, dust, and even smaller black holes. Around these enormous black holes, the remnants of stars continue to drift. Neutron stars, white dwarfs, black dwarfs, and free-floating planets move in long, slow orbits. Over trillions of years, gravitational interactions subtly nudge these objects, changing their paths. Some drift inward, pulled ever closer to the central black hole. Others are flung outward, drifting through the darkness beyond the galaxy's remnants. The motions are gentle, not dramatic, but over unimaginable spans of time, these tiny interactions accumulate. More and more matter finds its way toward the central black hole, feeding its growth. This era is not one of violent consumption. Black holes are often imagined as ravenous, devouring everything around them. But in truth, they are remarkably patient. Most objects orbit safely around them, untouched for trillions of years. Only those that wander too close cross the event horizon, joining the mass of the whole. Even then, the process is not a dramatic pull, but a quiet disappearance. The universe in this era is sparse. Matter is thinly distributed. Accretion disks, once bright and violent around young black holes, become rare. Instead, black holes grow slowly, quietly, by collecting the remnants of stars and the occasional drifting particle. Over time, the central black hole becomes the most massive object in its isolated region of space. It becomes the heart of the cosmic island. Everything remaining is held in its gravitational influence. By this stage, the universe has expanded so much that each island is entirely alone. No new galaxies will ever enter. No new light will reach across the void. Each isolated cluster evolves independently, shaped solely by its own matter and its own central black hole. The universe is now a collection of quiet, drifting archipelagos, each one anchored by a single gravitational well in the dark. As the trillions of years unfold, even the remnants change. Neutron stars may collide, forming more black holes. Black dwarfs may occasionally experience fusion triggered by quantum processes, adding tiny bursts of energy to the darkness. But these events grow rarer as time stretches on. Eventually, only black holes remain as the last significant structures. Everything else becomes thin radiation, sparse particles, and cold debris wandering through space. This marks the true rise of the era of black holes, where the universe's large-scale structure is defined almost exclusively by these dark, massive entities. Yet black holes are not eternal. Even they slowly change. Through Hawking radiation, a faint quantum process at the border of their event horizons, black holes very gradually lose mass. For large black holes, this effect is incredibly small. A black hole, the mass of a star, would take more than 10 to the power of 66 years to evaporate. A supermassive black hole might take longer than 10 to the power of 100 years, a number so large it defies familiar comprehension. During this time, the universe continues to expand, grow colder, and soften into stillness. The era of black holes is not a single moment, but an extraordinarily long chapter, one that stretches across more time than all previous eras combined. In the deepest reaches of this future, when the universe is dark and cold, and matter is scarce, black holes become like ancient monuments, silent, immense, and enduring. Their presence shapes the curvature of space-time. They hold the memory of all that fell into them. They persist in an environment where even starlight has long disappeared. To imagine this era is to imagine a cosmos stripped to its simplest form, islands of gravity, surrounded by an ocean of near-empty space. Each island anchored by a massive black hole glowing faintly with Hawking radiation. Those faint photons will be among the last sources of energy in the universe, drifting freely as the universe cools toward absolute zero. As time stretches beyond comprehension, even the black holes will eventually evaporate, one by one. Their final moments are not explosive, but soft, a brief increase in emitted radiation before they fade completely. When the last black hole evaporates, the era of black holes will end. What remains is a universe made only of scattered particles, faint radiation, and the quiet geometry of space-time. But in imagining this, we are reminded of the universe's long, gentle arc. The era of black holes is not a frightening future. It is a serene one, a period where the loudest processes of creation and destruction have calmed. It is the universe resting from its earlier brilliance, settling into a long, silent contemplation. And in that silence, we find a deep and peaceful beauty, a cosmos that endures, unhurried, shaped by gravity's patient hand, and softened by time's endless flow. 9. Hawking radiation, the soft breath of a vanishing whole. In the long, dim future when stars have faded and galaxies have grown quiet, the universe enters a period where the only intense gravitational structures remaining are black holes, vast anchors of space and time that formed from the collapse of massive stars and the merging of galaxies. These black holes drift within the sparse remnants of what were once vibrant cosmic communities. Around them, space is cold, dark, and nearly empty. Matter is scarce, light is rare. Interactions happen over time frames so long that even the most patient imagination struggles to grasp them. Yet even in this profound stillness, black holes are not truly eternal. They whisper their presence through a faint, delicate process known as Hawking radiation. This radiation is so gentle, so subtle, that it can be thought of as the last quiet breath the universe takes as it exhales into eternity. To imagine Hawking radiation, it helps to picture a black hole not as a vacuum or a bottomless pit, but as a region of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. This boundary is not a physical surface, but a line of no return. And yet, quantum physics, with its strange and delicate laws, reveals something unexpected. Black holes are not perfect prisons. They can emit a tiny amount of energy. This energy does not come from matter inside the hole, but from the quantum nature of space itself near the event horizon. Quantum theory tells us that empty space is never truly empty. It seethes with virtual particles that appear and disappear in pairs, flickering into existence for the briefest moments before annihilating each other. Normally, these pairs vanish instantly, leaving no trace, but near a black hole's event horizon, something remarkable can occur. If one particle of a virtual pair falls into the black hole while the other escapes, the pair is separated. The escaping particle becomes real, drifting away as radiation. The particle that falls into the black hole effectively reduces the hole's mass because it represents negative energy from the viewpoint of the universe outside. This process is what Stephen Hawking predicted. It means black holes are not completely black. They emit faint radiation that slowly drains their mass. The larger the black hole, the slower this process occurs. A black hole the mass of a star radiates so little energy that it would take 10 to the power of 66 years to evaporate many trillions of times the current age of the universe. A supermassive black hole, one with millions or billions of solar masses, would take even longer. It would persist for a duration that stretches beyond numbers we can comfortably imagine. Yet time, in these distant eras, becomes almost irrelevant. The universe is no longer governed by rapid cycles or bursts of creation. Everything moves at a pace that feels more like the slow unfurling of a sigh. And over these immense stretches of time, Hawking radiation becomes the gentle mechanism through which black holes gradually fade. Imagine the era of black holes, trillions upon trillions of years from now. The last stars have cooled into black dwarfs. Matter is thinly spread. Galaxies have merged into enormous, quiet ellipses that contain no young stars and no bright nebulae. Space is dark and cold. In this stillness, black holes continue their slow existence. They sit at the centers of their cosmic islands, or drift through the void as isolated remnants of collapsed stars. At first, the Hawking radiation they emit is so faint that it is almost meaningless. A typical stellar mass black hole emits almost no detectable energy. It loses mass at such a slow rate that its size remains effectively unchanged for unimaginable lengths of time. But as matter becomes scarcer in the universe, black holes feed less and less. There are no more gas clouds drifting near them. No more stars falling inward. No more galaxy collisions to deliver new material. The universe becomes a place where black holes no longer grow, they only shrink. Slowly, invisibly, delicately. As a black hole loses mass through Hawking radiation, it becomes slightly smaller. The smaller it gets, the hotter it becomes. And the hotter it becomes, the faster it emits radiation. This creates a feedback loop. In the earliest parts of this long process, the change is imperceptible. But as the black hole becomes small enough, its temperature rises noticeably, and the radiation becomes more energetic. Still, this phase lies so far in the future that the universe may be almost completely empty by the time it occurs. When a black hole has shed most of its mass, after countless epochs of slow evaporation, it enters its final stage. This stage is brief compared to the vast duration of its earlier life. The black hole becomes small, extremely hot, and radiates energy at a much faster rate. In its last moments, it emits a burst of radiation, a last flash of energy before it fades entirely. But this flash is not violent in the way we think of stellar explosions. It is subtle compared to the forces that once shaped the universe. It occurs in a cosmos so empty and dark that nothing nearby is present to witness it. The black hole simply evaporates, leaving behind a small amount of radiation that drifts into the expanding void. These final evaporations mark the end of the era of black holes. One by one, they vanish, their mass converted into gentle radiation. Even the most massive black holes eventually fade. The universe, once dominated by gravity and matter, transitions into a realm where only faint photons and thin, sparse particles remain. The great anchors of space-time dissolve, and the cosmos drifts further into stillness. Hawking radiation is, in many ways, a quiet reminder of the universe's impermanence. It shows that even the most enduring structures we know are not immortal. But it also reveals something softer. Black holes do not end in fury or collapse. They end in a whisper, a gentle release of energy, like the final exhale of a long-lived star. This subtle transformation mirrors the universe's overall path, from the blazing fire of the early cosmos to the cool quiet of the distant future. In this vision, the universe does not end abruptly. It softens, it fades, it cools. The disappearance of black holes through Hawking radiation is one of the last significant changes in a cosmos that has been unwinding for trillions of years. And in that fading, there is peace. There is a sense of completion, of the universe reaching its natural conclusion, not with drama but with serenity. Hawking radiation is more than a scientific prediction. It is a poetic idea. It tells us that even in the coldest, darkest future imaginable, there remains a faint breath of energy, a final glow. The universe, long after stars and galaxies and planets have passed from existence, still finds a way to exhale warmth into the silence. It is the soft breath of a vanishing whole, the last whisper of gravity's strongest expression. And through that whisper, the cosmos gently carries its final memories into the infinite, quiet, dark. Space expands, faster than light can cross it. In the present-day universe, when we look into the night sky, we see stars and galaxies arranged in a great cosmic panorama, a delicate pattern of light stretching across the blackness. To the human eye, this scene feels stable, almost permanent. The constellations shift slowly, gently. Galaxies beyond our own seem fixed in their places, distant and serene. But in truth, the universe is anything but still. It is expanding softly, continuously, and with a growing urgency. The space between galaxies stretches, the horizon of what we can see recedes. And though we do not feel this expansion in our everyday lives, its effects ripple outward across cosmic time, shaping the universe's fate in ways that are both profound and deeply calming. One of the quietest yet most transformative truths of cosmology is this: eventually, space will expand faster than light can cross it. This is not because light slows or struggles, but because the fabric of space itself is growing beneath it. Imagine walking across a floor that stretches faster than your steps can carry you. No matter how quickly you move, the expanding floor always creates more distance. Light, the fastest thing we know, faces the same quiet challenge in a universe ruled by accelerating expansion. This acceleration, driven by what we call dark energy, is one of the most mysterious features of the cosmos. Dark energy is not a substance or a force in the traditional sense. Instead, it is a property of space itself, an energy that does not dilute as the universe expands. While galaxies drift farther apart and matter grows thinner, dark energy remains constant. Its influence builds. Its quiet push becomes stronger relative to the pull of gravity. And in this way, the universe accelerates, not slowing down as one might expect from the mutual attraction of all matter, but speeding up, its expansion becoming more pronounced with time. This acceleration has already been observed. We see it in the redshift of distant galaxies, in the subtle stretching of ancient light. We detect it in the cosmic microwave background, the faint afterglow of the Big Bang, whose patterns reveal a universe being pushed outward. We have evidence not only that space is expanding, but that the pace of that expansion increases with time. And though this acceleration is gentle now, a stretching too subtle to feel on human scales, it becomes more significant as the universe ages. In the near future, on scales of billions or tens of billions of years, galaxies far from our own will drift away so quickly that their light stretches beyond the visible spectrum. They will fade from our view, sliding quietly beyond our cosmic horizon. Eventually, Only the galaxies in our local gravitational group, the merged remnant of the Milky Way and Andromeda, along with a handful of smaller companions, will remain visible. Everything else will drift so far away that no signal, no glimmer, no photon will ever reach us again. The universe will seem to shrink, not because it is contracting, but because expansion hides its distant parts from sight. Imagine a future observer living trillions of years from now. They might stand beneath a sky glowing only with the stars of a single, merged galaxy. They may detect faint remnants of radiation from long-gone events, but the broader universe, the rich web of galaxies and clusters that once filled their sky, will no longer be visible. They will see nothing beyond their own galactic island. Their cosmic horizon will have drawn inward so completely that the universe appears small, self-contained, quiet. They may never know that an immense expanse once lay beyond. This shrinking horizon is not a boundary in a physical sense. There is no edge, no wall, no barrier. The galaxies beyond our sight continue to exist. They continue to drift, evolve, and fade in their own isolated domains. But the expansion of space outpaces the ability of light to reach us. The horizon becomes a divide between what is knowable and what is forever beyond reach. It is a soft boundary, marked not by walls but by the gentle stretching of distance across time. As expansion continues, this effect grows even stronger. Eventually, the space between even nearby galaxies expands so quickly that light cannot cross the void between them. This does not tear galaxies apart. Gravity still binds stars into systems and systems into galaxies. But on larger scales, the fabric of space expands faster than any signal can travel. The distances grow not linearly, but exponentially. Every moment sees a greater separation than the one before. It is a quiet acceleration, but relentless. In the far future, well beyond the eras of stars and galaxies, the universe may enter a phase where each remaining cosmic structure becomes completely isolated, not just visually, but causally. No message can leave one island and reach another. No photon, no gravitational wave, no particle of any kind can cross the ever-widening void. The universe becomes a scattering of silent pockets, each one a lone bubble drifting in darkness. And within each bubble, the structure becomes simple. Perhaps a single black hole, perhaps a handful of remnants orbiting slowly, everything else having been flung outward or evaporated across time. This ultimate isolation is not a violent event. It is not a tearing or a rupture. It is more like the slow drifting of clouds across a vast sky, each one separating, dissolving into its own space. The universe expands like a breath that never fills again, and in this deepening stillness, space itself becomes so wide, so stretched, that even light takes longer than eternity to cross between islands. This leads to a profound shift in how the universe evolves. Expansion ensures that energy spreads thinner and thinner, cooled by distance, softened by time. Photons stretch into longer wavelengths until they lose nearly all their energy. Particles drift apart until they can go billions of years without encountering another. The universe cools toward absolute zero. Not suddenly, but gently, like the slow cooling of a once warm stone left in an endless night. This cooling is part of what cosmologists call the heat death of the universe, a state where all forms of usable energy have faded into equilibrium. But it is the accelerating expansion that ensures this final state becomes permanent. Without acceleration, gravity might one day begin to pull things inward again. Without acceleration, tiny fluctuations or dense regions might collapse into new structures. But dark energy ensures that expansion wins. It ensures that the universe continues to grow, continues to empty, continues to soften. Space expands faster and faster until every region becomes a quiet, isolated domain. Even light, our fastest messenger, cannot keep up. In this way, the universe becomes not a shrinking place, but an ever-expanding one that our senses can no longer follow. And yet, in imagining this far future, there is a profound tranquility. The expansion of space is slow, steady, and deeply calm. It does not erupt or collapse. It simply widens, gently and endlessly. It is the universe relaxing into its final posture, stretching into infinite stillness. And through this stretching, we glimpse the extraordinary patience of the cosmos, a world where even light, swift as it is, eventually yields to the vast, unhurried reach of time. In this distant horizon, where space outpaces even light, we find the universe settling into its most serene and spacious form, quiet, gentle, and endlessly unfolding. Matter becomes sparse and still. As the universe unfurls into deeper and deeper time, something subtle yet profound begins to take hold, not in sudden shifts, nor in explosive transformations, but in a long, serene unfolding. Matter, once vibrant, active, clumping into galaxies, birthing stars, igniting nebulae, begins to thin. It spreads out over expanses that grow wider with every passing epoch. Motion slows. Collisions become rare. The universe, after ages defined by dynamism and growth, starts to drift into a quiet stillness. This is the era when matter becomes sparse, when the cosmos settles into a state of calm so deep that change itself becomes a rarity. To understand this distant future, imagine stepping back to observe the universe as a whole. In its early stages, matter was dense and energetic. Quarks and gluons collided in a hot soup of creation. Later, atoms formed, galaxies condensed, stars ignited by the trillions, planets assembled from dust and rock. Everywhere, matter interacted with matter, fusing, cooling, collapsing, orbiting. The universe was alive with motion on every scale. But expansion has always been present, and with time, its influence grows, not because matter changes its nature, but because space itself continues to stretch, gently pushing everything farther apart. Over billions of years, galaxies drift beyond each other's horizons. Over trillions, stars burn through their fuel and fade. Over quadrillions, even the remnants of stars begin to cool, turning into dim, cold black dwarfs. And as expansion continues, the distances separating these remnants widen. A region of space that once held thousands of stars becomes home to only a handful. Eventually, those handfuls drift apart as well. With enough time, matter becomes diluted across such vast distances that most of the universe holds almost nothing at all. In this far future, the density of matter becomes astonishingly low. Not just thin, but truly sparse. A single particle might drift for billions of miles without encountering another. The universe becomes a desert. Its grains of sand spread so widely that the concept of proximity begins to lose meaning. The once crowded regions where stars formed spiral arms, dense nebula clusters, galactic cores grow quiet as the engines that powered them cease. Star formation dwindles to nothing. No new suns rise. No new planets form. Matter simply coasts, carried by expansion into a vast and widening sea of space. Inside each isolated galaxy, or whatever merged structure, remains after countless collisions and consolidations. A similar story unfolds. Stars have faded. White dwarfs have cooled. Even neutron stars, once the densest and most exotic of the star remnants, lose heat until they approach the temperature of the surrounding space. Black holes endure the longest, but even they slowly evaporate through Hawking radiation, losing mass drip by drip, photon by photon. With every passing epoch, the universe's supply of matter becomes more diffuse and more inert. Eventually, the universe reaches a stage where most of the mass is not held in stars or planets at all, but in individual particles. These particles, electrons, protons, if they remain stable, neutrinos, and the faintest dust grains drift apart endlessly. They rarely collide, they rarely interact. Motion continues, but with almost no consequences. A particle can carry a trajectory across vast distances without meeting another particle along the way. The universe becomes, in effect, a near-perfect vacuum. This thinning of matter brings with it a subtle quieting of physical processes. Without density, there is no pressure. Without pressure, there is no collapse. Without collapse, there are no new stars, no new structures, no new sparks of activity. Gravity still exists, as it always has, but its influence weakens as matter spreads out. The gravitational pull between distant particles becomes negligible. The forces that once shaped galaxies and stars no longer have enough mass in any given region to create new formations. The universe becomes dominated not by events, but by the absence of events, a great cosmic calm. In this calm landscape, temperature also approaches stillness. As expansion continues, the background radiation left over from the early universe stretches into longer and longer wavelengths. Its energy thins. Its warmth cools. Eventually, the temperature of space approaches absolute zero. Not the literal zero where molecular motion stops altogether. That limit may never be precisely reached, but close enough that almost nothing changes. The universe becomes a place so cold, so diffuse, that motion becomes smooth and uneventful. Energy differences flatten. Heat no longer flows from one region to another. Everything is in near-perfect thermal equilibrium. The slow cooling of matter in this future is gentle. There is no sudden freeze, no abrupt transformation. Instead, particles lose energy gradually as the universe expands. Each step is so small, it is imperceptible. But across unimaginable stretches of time, these tiny losses accumulate. White dwarfs fade, neutron stars mellow. Proton decay, if it occurs, takes its toll, slowly dissolving matter into lighter particles. If protons are stable, matter persists longer, but it still becomes less active, less capable of forming new structures. Whether matter dissolves or simply coasts, the result is the same: a universe slipping into perfect stillness. This stillness has its own kind of beauty. It resembles the quiet of a winter night, when snow absorbs sound and everything feels hushed. Except on a cosmic scale, the hush extends for trillions upon trillions of years. In this stillness, the universe no longer resembles the one we know. There are no glowing stars to punctuate the darkness, no swirling galaxies with luminous arms, no bright nebulae dreaming in the black. Instead, there are lone particles drifting through a vast, silent sea. Occasionally, two particles might meet in events so rare it would be the highlight of an epoch. But such meetings become exceptions rather than norms. And yet the universe persists. Even in this sparse, quiet state, it exists with a certain dignity. Every particle carries within it the history of the cosmos. The light that once streamed across galaxies now stretches into wavelengths so long they become soft whispers of energy. The structures that once shaped the universe's grand architecture leave behind a faint imprint in the curvature of space. Nothing moves quickly, nothing burns, nothing forms, but everything continues, drifting, waiting, resting. This vision of the universe may feel lonely to us, accustomed as we are to a cosmos filled with light and life. But there is a profound peace in imagining the far future as a place of stillness. The universe has spent trillions of years in motion, colliding, forming, exploding, cooling. Its history is one of extraordinary dynamism. At last, it rests. At last, it settles into a quiet equilibrium, And while this state may seem like the end of activity, it also represents a kind of cosmic maturity, the final stable chapter of matter's long and intricate journey. The sparsity of matter is not an ending in the emotional sense. It is a natural outcome of the universe's expansion. It is the universe exhaling fully, allowing everything to drift apart and cool. And in that infinite drift, there is no suffering, no conflict, no turmoil. There is only space-wide, peaceful, and unhurried, a universe that has grown old, quiet, and gentle. In this distant future, matter becomes sparse and still. But in that stillness, the universe achieves a calm, unmatched by any previous era, a quiet, so deep it carries the memory of everything that came before, whispering gently into the endless dark. 12. The faint glow of the last interactions. As the universe drifts deeper into its quiet, expanding future, the vast structures that once defined it, its galaxies, its stars, its bright nebulae and warm clusters, have all softened into memory. What remains is a cosmos pared down to its essentials: cold remnants, thin particles, and soft radiation stretched across unimaginable distances. The bustling interactions that once animated the universe's early eras have faded. Yet even in this great stillness, there are moments rare, delicate, almost ghost-like, when particles meet, when energy stirs, and when the universe produces the faintest glimmers of light. These final interactions, occurring in a cosmos that has grown calm and sparse, offer the universe's last whispers of activity before darkness becomes complete. To imagine this era, picture a space so wide and thin that a single atom might travel tens of thousands of miles before encountering another. Space is no longer a medium where matter clumps or forms structures. It is an ocean of almost perfect emptiness. And yet, emptiness in the cosmic sense is never absolute. Even at near absolute zero temperatures, particles continue to move, drifting through the vastness with slow, silent persistence. They carry within them remnants of past energies, past interactions, past eruptions of creation. These particles, electrons, neutrinos, photons, and perhaps whatever fundamental components remain after proton decay, are the last actors in the universe's long play. The term, the faint glow of the last interactions, reflects these final sparks of activity. Not enough to light galaxies, not enough to warm worlds, not even enough to fill space with a noticeable haze. Instead, they are like the last embers of a campfire, glowing faintly under a blanket of ash. They do not reignite, they do not flare, they merely persist, soft and quiet, offering a subtle reminder of the energetic universe that once existed. One of the primary sources of these faint glimmers comes from what remains of matter's natural tendencies to interact. Even in a universe where matter is sparse, particles still collide occasionally. Rare events that may take place once in many trillions of years within a given region. When two particles meet, they may annihilate, releasing tiny quanta of energy. Photons produced in these interactions drift outward, stretched by cosmic expansion into wavelengths so long they become almost indistinguishable from the background. They carry almost no heat, no momentum, and no structure, but they persist, the faint glow of ancient processes echoing in an otherwise quiet sea. Another source of these last interactions comes from the slow decay of particles themselves. If protons decay as some theories propose, they do so with half-lives spanning unimaginable time intervals. A proton might survive for 10 to the power of 34 years or far longer, but given enough time, even these stable particles would eventually break apart. Each decay releases a small amount of energy, producing lighter particles that drift apart and contribute to the faint radiation that fills the universe. If protons are immortal, the universe's supply of matter would persist. But even then, matter slowly loses cohesion, spreading thinner until the likelihood of interaction approaches zero. Yet even in this slow decay, the universe displays gentleness rather than sudden transformation. The disappearance of matter is not a cataclysm, but a gradual softening. Each decay is a whisper, a quiet transition. Tiny flashes of light, far too weak to illuminate anything, appear and then stretch into the cosmic darkness. The universe does not resist this process. It allows its components to fade naturally, steadily, in perfect calm. There are other glimmers too, born from the rare motions of collapsed remnants, black dwarfs, cooled remnants of stars that no longer shine, may occasionally experience quantum tunneling deep within their cores. Over time scales so long they defy normal comprehension. Carbon atoms within these black dwarfs could fuse due to quantum effects, releasing minuscule bursts of energy. These events would be extraordinarily rare and dim, far weaker than any star that came before. But they would still be moments of light, tiny sparks marking the quiet conclusion of stellar evolution. They would represent the last breaths of nuclear activity in the cosmos. Then there are the interactions tied to gravity. Though matter has become thin and cold, gravity never disappears. It continues shaping the distribution of particles, guiding them into gentle paths. Even in the late universe, gravitational encounters between drifting remnants can produce tiny flashes of energy. When two dead stars or remnants wander close enough, they may emit faint gravitational radiation or, in extremely rare cases, collide. These collisions, though vastly less violent than those of earlier cosmic epochs, would still create small releases of light and heat. But such events are so improbable in the late universe that a single collision might be the rarest event across countless trillions of years. Another source of the universe's faint glow comes from Hawking radiation, the soft breath emitted by evaporating black holes. As these ancient remnants shrink and warm, they release small amounts of radiation. At first, this radiation is almost imperceptible. But as black holes become smaller, their evaporation accelerates, producing slightly more energetic photons and particles. In their final moments, the radiation brightens slightly, not into anything brilliant, but into a modest glow compared to the quiet background. When the last black hole evaporates, its final whisper of radiation will be one of the last luminous events in the universe. These final interactions carry profound poetic weight. They represent the universe's last expressions of activity, its last flickers of change, its final sparks in the long night. They do not resemble the energetic, dynamic processes of earlier eras. Instead, they are soft, whisper-like, solitary. They are reminders that even in great stillness, the universe continues to evolve, guided by laws that persist across the deepest reaches of time. As these interactions become rarer, the cosmos drifts into increasing equilibrium. Heat cannot flow where temperature differences vanish. Particles cannot collide where distances are immeasurable. Processes slow, then slow further, then slow further still. Eventually, the faint glow itself begins to fade. The radiation spreads so thinly that even detecting a single photon becomes an improbable miracle. The universe transitions into an era where interactions cease almost entirely. Each region of space becomes a calm, empty expanse of near-perfect stillness. And yet, this stillness is not frightening. It is not a void in the emotional sense. It is a peaceful settling, a universe that has lived through fire, light, birth, collapse, and growth, finally returning to rest. The faint glow of the last interactions is the universe's gentle farewell to activity. It is the soft, final heartbeat of a cosmos that once burst with energy. In imagining this era, we glimpse the full arc of cosmic time from dazzling brilliance to quiet dissolution, and through that arc, we discover a profound serenity. The universe does not end abruptly. It fades softly, gently, lovingly. Its final glimmers are delicate reminders of all that came before, drifting into an endless, peaceful night. 13. The decay of atoms begins. In the deep future of the universe, long after the last stars have faded and the vast structures of galaxies have drifted apart, the cosmos enters a phase defined less by motion and light and more by quiet endurance. Matter, once the building block of everything from stars to planets to living beings, continues its slow existence in forms far simpler than any we know today. But even this simplicity is not eternal. For in the distant reaches of time, a subtle and gentle process may unfold, the decay of atoms themselves. It is a process so slow, so delicate, and so patient that it stretches beyond familiar measures of time. Yet if it occurs, it marks one of the final transitions in the universe's long, gentle journey towards stillness. To imagine the decay of atoms, we begin by recalling how matter is structured today. Every object we can touch or see is made of atoms, tiny systems with a small central nucleus of protons and neutrons, surrounded by a cloud of electrons. This arrangement has endured for billions of years without noticeable change, forming the foundation of chemistry and the structure of all physical matter. In the present universe, protons, the positively charged particles inside the nucleus, seem perfectly stable. They have never been observed to decay. And yet some theories in particle physics suggest that protons might not be truly eternal. They may have incredibly long half-lives, so long that decay has never been witnessed. But across the unimaginable timescales of the late universe, even the improbable becomes possible. If proton decay occurs, it would be a process of extreme subtlety. One moment, a proton would exist as it always has. The next, it would quietly transform into lighter particles, perhaps a positron, perhaps a pion, before those two drift apart into the faint sea of radiation that fills the expanding cosmos. This transformation would not be violent. It would not shatter anything in a dramatic burst. Instead, it would be like the quiet release of a particle's last stored energy, a soft sigh of existence, letting go into the surrounding emptiness. Should this process unfold, it would alter the universe in slow, gentle ways. Atoms, which rely on protons for their identity, would slowly dissolve. Hydrogen, the simplest and most abundant element, would vanish first. Heavier atoms, composed of multiple protons, would linger longer, but they too would eventually fade. A carbon atom, for instance, would lose its protons one by one, each decay subtly shifting its structure until the atom could no longer hold together. Over astonishing spans of time, all matter would gradually disassemble into lighter components, particles that drift endlessly, unable to bind into anything more complex. It is difficult to imagine this process because atoms feel elemental to us, fundamental and unchanging. But in the far future of a cooling universe, the stability we associate with matter may not hold. The decay of atoms is not a destructive act, but a long, gentle unweaving of the fabric of matter. It is a silent, gradual return of complex structures into simpler forms. And this return mirrors many of the universe's other transformations. Stars collapsing into remnants, galaxies dispersing into isolated islands, black holes evaporating into faint radiation. Over and over, complexity yields to simplicity, not in anger or violence, but in calm surrender. If protons do decay, the timeline is staggeringly long. The half-life may be around 10 to the power of 34 years or more, far beyond the timescales of stars, galaxies, or even black holes. But the universe is patient. It stretches into epochs where numbers lose their meaning. Across these incomprehensible ages, proton decay would gradually remove the remaining structure from the cosmos. Matter that once formed planets and life, that once glowed in the hearts of stars, would dissolve into an almost featureless sea of radiation and subatomic particles. But suppose protons are stable. Suppose they never decay. Even then, the universe still drifts toward simplification. Atoms would continue to exist, but they would be separated by expanding space, colder and more isolated than ever before. They would lose energy, not through decay, but through the ongoing expansion that stretches their wavelengths and cools their surroundings. Electrons might eventually be stripped away by random interactions or cosmic expansion, leaving cold nuclei drifting alone through a vast, silent void. Whether through decay or cooling, atoms face a future where they become inert, scattered, and isolated. Their interactions cease, their structure becomes static, their role in shaping the universe dims into stillness. If proton decay does occur, the transformation of matter leads to an era where the universe is filled with lighter particles, electrons, positrons, neutrinos, and photons with wavelengths longer than galaxies once were. These particles carry tiny amounts of energy, drifting farther apart with every second of cosmic expansion. The remnants of atoms become mere whispers in the dark, traces of the universe's once complex structure. The cosmos becomes simple again, stripped down to its most fundamental ingredients. In this era, the very idea of matter becomes almost poetic rather than physical. A single proton that survives into the far future represents a rarity, a relic from the universe's youth. Each decay is a reminder of time's vastness, of the gentle patience with which the cosmos unwinds its own structure. Nothing in this future is rushed. Nothing collapses in urgency. There is only the long, tranquil unweaving of complexity. And through this unweaving, the universe grows more still. Motion becomes smooth. Interactions become rare. Energy that once fueled the processes of creation disperses into an endless expanse. The temperature of space approaches absolute zero, though it never quite reaches it. Everything slows until change becomes almost indistinguishable from rest. The decay of atoms, should it happen, marks one of the universe's last significant transitions. It is the quiet fading away of the structures that once generated stars, planets, and life. It is not annihilation but transformation, matter returning to the faintest forms of energy, like the last notes of a long symphony drifting into silence. And even if protons remain stable forever, the outcome feels similar. The universe still ages, still drifts toward equilibrium, still softens into a vast, cold sea, where atoms exist but rarely interact. There is a peacefulness in this vision. The universe ends not in fire, but in cool dissolution. It does not collapse or explode. It unwinds. It breathes out its last structures into a calm so deep it is almost sacred. The decay of atoms, or their gradual quieting, is simply the final step in a long journey from cosmic fire to cosmic stillness. And in that stillness, the universe rests. It rests after trillions upon trillions of years of motion, light, heat, and transformation. It rests in a darkness that is gentle, expansive, and complete. The atoms that once built everything dissolve into a soft, pervasive quiet, leaving behind a universe that has finally reached the simplest, most peaceful form it can achieve. 14. The universe settles into a thin mist of light. As the universe travels further into its unimaginable future, moving far beyond the eras defined by stars, galaxies, and even atoms, it undergoes a final softening. The transitions that shaped its vast history, the births and deaths of stars, the merging of galaxies, the fading of remnants, the cooling of cosmic radiation, have all played their roles. What remains is an elegant simplicity, a cosmos no longer built from shining spheres of gas or grand spirals of countless suns, but instead composed of something quieter and more ephemeral. The universe becomes a thin mist of light, so faint, so diffuse, and so gentle that it drifts almost unnoticed across the vast, dark canvas of expanding space. This mist is not the radiant glow of starlight. It is not the warm background that once filled the universe in its infancy. Instead, it is the collective whisper of all the processes that came before the residue of interactions, decays, and evaporations, stretched thin over distances that have grown larger than galaxies once were. Every particle of light in this future carries with it a memory, the flash of a dying star, the faint release of energy from a decaying atom, the last breath of an evaporating black hole. These photons drift freely, with no structures left to capture them, no atoms to absorb them, no stars to block their passage. They spread outward endlessly, gradually thinning as space expands, becoming a faint, pervasive haze. To envision this thin mist, imagine standing in a dark, silent field under an almost moonless sky. The air is still. The world around you barely reveals itself. Yet there is a subtle sense of presence, a quiet, diffused glow that suggests something drifting through the unseen. Now expand that feeling across the entire universe. The mist of light that remains is not bright enough to illuminate anything. Yet, it is not entirely absent. It is the softest possible form of radiation, filling every region of space with a quiet reminder of its long history. In the current universe, light has form and function. It warms planets, illuminates galaxies, and carries information across immense distances. But in the far future, the purpose of light becomes simpler. It merely persists. These photons, each one stretched to unimaginable wavelengths by the continued expansion of space, glide silently through an almost perfect vacuum. Their wavelengths become so long that they no longer resemble the light we know. They are not blue or red, not visible or infrared. They are soft ripples in space-time, waves so gentle that they can span entire galaxies or exceed the horizon of observable space. The universe's expansion ensures that this mist becomes increasingly thin. As space grows, the density of photons, the number of them per region of space, decreases. Their energy diminishes as well, stretched further by the unrelenting expansion. Every moment sees them become a little colder, a little slower in their vibration, a little less energetic. Even the cosmic microwave background, once a warm glow left over from the early universe, cools into radio waves, then into waves with wavelengths measured in light years. Eventually, it becomes so diffuse it blends seamlessly with the faint radiation from decays and evaporations. This thinning mist is not entirely uniform. In the earliest phases of the far future, remnants of structure still remain. There are regions where black holes evaporate, emitting slightly more energetic photons. There are regions where the last remnants of matter undergo rare interactions, releasing tiny bursts of energy that contribute to the mist. But as time stretches forward, even these differences fade. Black holes evaporate completely, with the largest ones releasing their last radiation in quiet, gentle bursts. Proton decay, if it occurs, gradually transforms all remaining matter into this faint mist of particles. And the entire universe becomes something like a vast, calm ocean, filled not with water, but with waves of light so stretched and cool that they carry almost no heat at all. In this future, the universe approaches thermal equilibrium, a state where energy is distributed so evenly that no region rises above another. Without heat differences, without dense concentrations of mass, without the engines that once fueled cosmic evolution, the cosmos enters its final stage of quiet balance. The thin mist of light no longer changes significantly. There are no new sources of brightness, no new bursts of activity, no new flows of energy from one place to another. The universe becomes a calm, almost unchanging sea, with photons drifting like dust motes in a vast, abandoned cathedral. And yet, this final state is not devoid of meaning. The light that remains carries the echo of everything that once was. Each photon, stretched and softened though it is, comes from a moment in the cosmos's long past, the final radiation from a dying black dwarf, the glow from a particle decaying in unimaginable silence, the gentle evaporation of a black hole that once anchored a galaxy's heart. All of these faint signals, though indistinguishable from one another in the late universe, are pieces of the same cosmic memory. The thinning of light also represents the final transition from a universe of activity to a universe of calm. In the early cosmos, energy was concentrated, interactions were frequent, and temperature differences drove the processes of creation. Stars lived and died violently. Galaxies collided and reshaped the darkness. Black holes formed, consumed, and merged. Everywhere, energy surged and flowed. But as the universe ages, these variations disappear. Energy spreads evenly. Light becomes uniform and soft. The sharp contrasts fade into a gentle harmony. There is a beauty in this calmness. For billions of years, the universe was a place of constant motion, swirling, bright, turbulent. Its structures formed and collapsed like waves. But all waves eventually settle. What remains at the end is a stillness that is not emptiness, but rest. The thin mist of light becomes the universe's final resting place, a soft and quiet background that holds the memory of every motion that ever occurred. This final glow does not illuminate, it does not warm, it does not interact with anything at all, but it is there, filling space with a sense of quiet presence. It is the universe's last light, gentle, stretched, and calm, a soft exhalation after a lifetime of brilliance. As time stretches further, the mist becomes even thinner. Eventually, photons become so widely spaced that they rarely encounter anything. They drift through emptiness with no chance of absorption, no chance of interaction. They simply move forward, their wavelengths continuing to stretch as the universe expands. The cosmos becomes a place where even light seems to slow, not in speed, but in rhythm. This is the universe settling into its final form, a peaceful, soft, ever-expanding sea of faint radiation. No storms, no stars, no galaxies, only the thinnest mist of light drifting through silence. And in that silence, the universe finds its final peace, a gentle, enduring calm that stretches into eternity. 15. The stretching of light into eternity. As the universe moves into its most distant future, long after galaxies have drifted apart and matter has grown thin, one quiet process continues without pause: the stretching of light. It is a transformation so gentle, so patient, and so endlessly persistent that it becomes one of the last active rhythms in a cosmos, otherwise settling into stillness. Every photon born in the early universe, every glimmer released by stars that once lit the night, every faint glow from collisions and decays, continues traveling outward. And as it travels, space itself expands beneath it, lengthening its waves, thinning its energy, and softening its existence until light becomes something more like a whisper than a wave. This gradual stretching of light is subtle at first, barely noticeable over human timescales, but across the deep ocean of cosmic time, it becomes one of the most defining features of the universe's later eras. To understand this cosmic stretching, imagine light as a series of gentle ripples moving across the surface of an infinite lake. Now imagine that the lake itself is widening, expanding outward in all directions. As the water stretches, each ripple spreads out with it. Its peaks grow farther apart, Its energy spreads thinner and thinner across a larger surface. In the universe, this stretching is not caused by water, but by the expansion of space-time itself. When light travels through expanding space, its wavelength increases. Blue light becomes redder, red light becomes infrared, infrared radiation becomes microwave, then radio. Eventually, the wavelengths become so long that they stretch across distances larger than galaxies once were. This transformation is not destructive. It is not a tearing or a weakening in the violent sense. Instead, it is a softening, a gentle relaxation of the light's structure. Each photon simply adjusts to the expanding fabric of the universe, lengthening in harmony with the space it occupies. At every moment, the photon remains exactly what it is, just stretched, cooled, and slowed in its rhythm. As expansion continues, the photon carries less and less energy, becoming an ever fainter echo of its original form. One of the most beautiful aspects of this process is that it preserves memory. A photon of light emitted by a star billions of years ago still travels outward today. Though its wavelength has changed, though it has cooled and softened, it carries with it the story of where it came from. In its earliest moments, the universe was filled with bright, energetic light. That light has never disappeared. It has only transformed, stretched across vast distances until its glow becomes the faintest mist drifting through space. And even when galaxies have faded and stars have died, those photons continue their quiet journey, lengthening into eternity. As the universe ages, expansion accelerates. Dark energy, the mysterious force that drives the growth of space, becomes increasingly dominant. This acceleration ensures that the stretching of light becomes more dramatic over time. In the near-future universe, photons will continue to redshift into wavelengths too long for any eye or instrument to detect. The cosmic background radiation, once warm with the heat of the early universe, will cool until it becomes a faint, nearly undetectable hum. Photons emitted by the last stars will eventually stretch into wavelengths so long they carry almost no distinguishable energy at all. They will not disappear, but they will become so diffuse that they fade into the cosmic stillness. The stretching of light also reshapes how the universe appears. In the present era, the night sky is alive with distant galaxies, each sending light across vast distances to reach us. In trillions of years, those galaxies will slip beyond the cosmic horizon. Their light will continue to travel, but expansion will outpace it. The photons will stretch so much that they will never arrive. Even the photons already on their way will become so elongated and faint that they dissolve into the expanding space long before reaching any observer. The universe grows visually quiet, not because the galaxies vanish, but because their light can no longer cross the widening gulf between us. In the far future, what remains of light becomes more ephemeral. Photons, originally emitted with high energies, may become stretched to wavelengths longer than entire galaxy clusters. A single wave of light could span distances that were once filled with stars and galaxies. This enormous wavelength does not make the light weaker in presence, only in energy. The photon is still there, still traveling, still part of the cosmic fabric, but it no longer resembles light as we know it. It has become more like a slow undulation across the vast sea of space-time. This stretching continues indefinitely. In the extraordinarily distant future, photons become so diffuse, so spread out, that their individual identities blur into a nearly uniform background. The universe becomes filled with these long, slow waves, drifting in perfect calm. Their energies are so low that they no longer contribute to any physical processes. They no longer heat, illuminate, or interact. Instead, they exist as remnants of ancient activity, quietly filling space with an almost immeasurable presence. Eventually, the universe reaches a stage where the stretching of light approaches its ultimate expression. Wavelengths become so long, they no longer fit within any single region of the universe that can be considered connected. Photons lose their coherence as individual waves. They blend into the geometry of space, leaving behind only the faintest imprint of energy. At this point, light is no longer something that travels. It becomes a soft, ever-present background, a final whisper of the universe's distant past. But even in this near-perfect stillness, there is beauty. Light, the universe's most expressive storyteller, does not vanish violently. It fades gently, gracefully, with a patience that mirrors the expansion carrying it forward. Each photon stretches, carrying its memory into the future, becoming softer and softer until it merges with the quiet of space. The universe does not extinguish light, it simply transforms it into a calm, endless exhale. The stretching of light into eternity is one of the universe's most poetic processes. It reminds us that nothing in the cosmos truly disappears. Energy changes form, memory shifts into gentler expressions. The bright brilliance of the early universe becomes the faint hum of the late one. Light, once an agent of warmth, creation, and motion, becomes a soft companion to a universe that has grown old and peaceful. And in that peace, the stretched photons continue their silent drift, carrying the echo of every luminous moment across an infinite horizon. They ask nothing, they illuminate nothing. They simply persist, gentle reminders of a universe that once shone brightly, now resting quietly in the long night of eternity. 16. The heat death, perfect stillness. As the universe drifts deeper into its unimaginable twilight, after stars have vanished, after black holes have evaporated, after atoms themselves have unraveled or fallen into cold stillness, a profound quiet takes hold. Not a quiet born of silence, but a quiet born of balance, of everything reaching a state so even, so uniform, so perfectly diffused that nothing meaningful can change anymore. This is the heat death of the universe, one of the calmest ideas ever imagined in cosmology. It is not a single moment, not a sudden collapse or a catastrophic ending. Instead, it is an arrival, slow and inevitable, like the settling of dust after a long journey. A deep, vast stillness spreads across all of existence, marking the universe's gentle transition into a final rest. To imagine the heat death, it helps to think about what drives change in the cosmos today. Stars shine because hydrogen fuses into helium, releasing energy from areas of high temperature into surrounding cooler space. Galaxies evolve because matter collapses under gravity, forming structures that alter their surroundings. Even the early universe changed because it began as a hot, dense state and gradually expanded into cooler, less dense forms. Every process relies on differences in heat, differences in density, differences in pressure. Where there are contrasts, there is motion. Where there is motion, there is change. But as the universe ages, these contrasts fade. Expansion spreads matter thin. Light stretches into softer and softer wavelengths. Stars burn out. Black holes evaporate. And even the last remnants of matter grow cold. Energy disperses throughout space until no region holds more than another. Temperature differences eventually smooth out across the cosmos. This absence of difference, this leveling of all gradients, leads to a state where nothing compels anything to move or transform. It is not that motion becomes impossible, but that no meaningful motion remains. The universe approaches equilibrium, the calmest physical condition imaginable. We can think of heat death as the universe's final exhale. It is the point where energy is so evenly distributed that it can no longer flow from one place to another. Without that flow, processes that once shaped the cosmos can no longer occur. Stars cannot ignite. Galaxies cannot form. Chemical reactions cannot spark. Even the rare interactions of particles become sparser and less significant until they cease to change anything at all. What remains is a cosmic environment of near-perfect stability, with temperature hovering just above absolute zero, and matter spread so thinly that the concept of structure becomes almost meaningless. The journey to this state is long beyond comprehension. It begins in the era we currently inhabit, when stars still shine and galaxies still thrive. Over trillions of years, those stars age and fade. Galaxies lose their light, becoming mostly collections of remnants, white dwarfs, neutron stars, and black holes. Much later, after countless more epochs, even those remnants undergo change. White dwarfs cool, neutron stars lose their residual heat, black holes evaporate slowly through Hawking radiation. With their evaporation, one of the last concentrated forms of energy disappears, leaving behind only a faint mist of particles and photons drifting through nearly empty space. As expansion continues, even this faint mist stretches thinner. Photons redshift into almost unmeasurable wavelengths. Particles drift farther apart. Collisions become so rare that a single interaction might take longer than the current age of the universe, multiplied by staggering factors. On these scales, the universe loses its dynamism. It becomes a place where events no longer unfold in meaningful sequences. The concept of before and after becomes less useful, because no distinguishable process remains to mark the flow of time. In this late stage, the universe resembles an enormous, quiet ocean whose waters no longer move. Not because they are frozen, but because they are perfectly still, completely uniform, without currents or waves. Every region is nearly identical to every other. The last traces of heat have been stretched and smeared across space, until they blend into an almost indistinguishable background. Time continues, but it flows through a cosmos where nothing changes with it. Yet the heat death is not something to fear. It is not a tragic ending. It is simply the natural destination of a universe governed by the laws of thermodynamics. If anything, it is soothing in its inevitability. The universe has spent an eternity in motion, creating, destroying, heating, cooling, igniting, fading. It has endured cycles of extraordinary brilliance, stars blazing in the darkness, galaxies spinning in elegant spirals, black holes shaping the fabric of space. It has experienced epochs of intense drama, from the explosive birth of the early universe to the quiet aging of later eras. After such an immensely long and active story, the universe's gradual settling into stillness feels like a peaceful return to rest. One might imagine this final stillness as the surface of a calm sea at dusk, not empty but untroubled, not silent but serene. The universe, after unfolding in complexity for trillions upon trillions of years, allows itself to relax into a state where no more work can be done, where no more heat can flow, where all that remains is the quiet presence of the last scattered particles drifting through an ever-expanding expanse. In this state, even the definition of space changes. Distances grow so immense that the concept of connection becomes abstract. Particles may drift within sight or within theoretical reach of nothing else for unimaginable lengths of time. Their existence becomes solitary, not through isolation imposed by barriers, but through the sheer wideness of the universe. And yet, there is no suffering in this solitude, because the universe itself has no needs left unmet. It has reached a perfect stillness. The heat death is sometimes described as the end of the universe, but that word does not fully capture its nature. It is not the end in the way a story concludes or a flame is extinguished. Instead, it is a transformation into a new state, a state of gentle uniformity, of quiet equilibrium, where the universe continues to exist, but without contrast, without events, without change. It continues to expand, to stretch, to drift toward an even deeper stillness. But in its essence, it has reached a place where its long journey has softened into rest. And in that rest, there is beauty. The heat death is the universe's most peaceful moment. A moment not of collapse or violence, but of balance so complete that it resembles a cosmic meditation. A universe that began with overwhelming brightness and heat ends with a soft whisper of cool, even calm. And that calm is not empty, it is the quiet memory of everything that ever was, stretched gently across the vastness of eternity. In this perfect stillness, the universe finds the deepest peace it has ever known. It becomes a vast, quiet canvas, holding the echoes of all its earlier light, all its earlier movement, all its earlier stories, now softened into the most tranquil state imaginable. A universe at rest, breathing no more, but existing gently in the long night forever. 17. Time loses its meaning, where nothing changes. As the universe drifts into its deepest, most tranquil future, after all the lights have faded and all the structures have dissolved, something subtle and profound begins to unfold, not in space, but in the very idea of time itself. Time, which once pulsed with the rhythm of stars, planets, collisions, and transformations, begins to soften, to blur, and finally to lose its meaning. In a cosmos where nothing changes, where energy no longer flows, where matter no longer clumps or moves or interacts, time becomes less a river and more a still pool. It becomes a dimension that remains, but without purpose, an empty stage long after the actors have departed. To understand how time changes in this final era, we must remember what time has always been. Time is not an external force moving the universe forward. Instead, time is the measure of change. We perceive the passage of time because things around us evolve, stars burn, planets orbit, atoms collide, thoughts form and dissolve. Time is the thread connecting these moments, the sequence that stitches together cause and effect. Without change, time loses its anchor. Without events, time becomes hard to distinguish from eternity. In the universe's earliest days, time flowed with astonishing intensity. Matter and energy collided violently. Temperatures soared and plunged. Structures formed in rapid succession. Everything was in motion. Time was active, visible, measurable, everywhere. As the universe aged, time began to stretch outward alongside space. Processes slowed. Stars lived for billions of years instead of the few minutes that shaped the earliest particles. Galaxies drifted apart in motions so gradual, they seemed frozen from any human perspective. Time did not weaken, but the rate of change softened. Each cosmic event required more time to unfold than the ones before. Now imagine the universe after the heat death, after equilibrium has settled across all existence. Every region of space sits at nearly the same temperature. No heat flows, because there are no warmer or colder places left. No structures form, because matter has spread so thin that gravity can no longer gather it. No stars shine, no black holes feed, no atoms rearrange. What remains is a vast and nearly unchanging ocean of cold, thin radiation and scattered particles drifting gently through the quiet. Every corner of the cosmos looks nearly identical to every other. In this environment, time still exists. In theory, we can label moments, assign coordinates, imagine sequences. But without change, time's function dissolves. Consider a perfectly still lake. The water exists, the surface is present. But without ripples, wind, or currents, it becomes impossible to measure the passage of time by observing the lake itself. The universe in its final stillness becomes something like this lake. It holds the memory of time, but no longer expresses it. Even the smallest processes that once marked the flow of time have ended. All known particles have either decayed or become inert, Photons have stretched into wavelengths so long they barely carry energy. Motions occur so infrequently that they are meaningless in any useful measure. A particle drifting through space might not collide with another for more years than there are atoms in the observable universe. A single interaction could take longer than the age of everything that came before combined. These rare events are so isolated that they cannot define a rhythm, cannot mark progression, cannot give shape to time. In this late era, the universe approaches a kind of temporal horizon. Time may continue to exist as a theoretical dimension, much like width and height, but becomes unobservable because no processes remain to reveal its passing. This is one of the most profound aspects of the universe's long future. The cosmos does not merely become dark or empty, it becomes temporally silent. The clock of the universe continues to tick, but no hand moves, no shadow shifts, no energy transfers. It becomes impossible to distinguish one moment from the next because nothing changes from one to the other. This idea is not meant to suggest that time stops in a literal sense. Rather, it becomes irrelevant. It becomes a concept without examples, a story without events, a path without footsteps. Even now, in the present universe, time feels slower in regions where little change occurs. A mountaintop seems timeless compared to a rushing river. A barren desert feels still compared to a bustling city. Scale these impressions outward by uncountable orders of magnitude, and you approach the temporal serenity of the heat-dead cosmos. Yet this stillness is not unsettling. It is peaceful. It is the ultimate quiet after an eternity of motion. The universe has burned, collided, created, destroyed, formed stars, sculpted galaxies, and woven the fabric of matter into endless shapes. It has experienced ceaseless dynamism for trillions upon trillions of years, and now, at last, it rests. Picture this final universe in your mind. No light to mark a sunrise, no stars to track across the sky, no movement to measure. Only a vast, soft darkness filled with the faintest traces of radiation and the rare drift of a lonely particle. The silence is not absence, but completion, the natural consequence of a universe that has given all its energy away, that has spent itself fully. Time, in this quiet infinity, becomes something more like a backdrop. It remains present, but without motion or contrast, it becomes almost indistinguishable from eternity. One could imagine standing in this cosmic silence and asking how much time has passed, but the universe would offer no answer, because there would be no change to reference, no before or after to compare. In this final state, time becomes a canvas with no painting, a melody with no notes, a story that continues but no longer unfolds. And yet, through this stillness, the universe retains dignity. It holds the echo of everything it has ever been. The memories of every star, every galaxy, every moment of creation are not lost. They are diffused into the thin radiation that remains, carried within photons, stretched to impossible lengths. These photons, though quiet, are remnants of a vibrant past. They are the faint traces of everything the universe once was, drifting indefinitely through a realm where time's meaning has dissolved. This gentle dissolution of time is perhaps the most peaceful image in all of cosmology. The universe does not end with a final event or a sudden collapse. It fades into a state where even time becomes soft, where moments cease to differ, where the cosmos rests in a deep and infinite calm. And in that calm, the universe continues not as a place of events, but as a place of pure existence, a place where time is no longer the measure of motion, but the silent companion of a cosmos that has finally settled into eternal rest. 18. The quiet geometry of a fading cosmos. As the universe slips deeper into its final eras, long after stars have dimmed and matter has dissolved into a thin, drifting mist, something subtle remains quiet, yet profound. Even when nearly everything else has faded, the universe still holds its shape. Not the shape of galaxies or clusters or constellations, but the shape of space-time itself. This geometry, the fabric upon which all cosmic stories were once written, persists like a soft imprint, long after the events that created it have disappeared. In this deep future, the universe becomes less a place of objects and more a place of gentle curvature, a vast and nearly empty landscape defined by the faint, lingering echoes of all that came before. To understand this quiet geometry, it helps to imagine space not as an empty stage, but as a surface that can bend, stretch, and curve. Gravity, in Einstein's view, is just the curvature of space-time caused by mass and energy. A star bends space around it. A planet creates a small dimple beneath it. A galaxy produces a vast well where orbits form. Even a single photon leaves a subtle imprint as it glides through the cosmos. These curves and bends shape the experience of everything within the universe, even in the far future when the actors have exited the stage. But as time stretches endlessly forward, mass itself becomes scarce. Black holes evaporate. Atoms decay or become inert. Particles drift apart until no region contains enough matter to produce meaningful curvature. And yet, space-time does not instantly flatten. The geometry of the cosmos evolves just as gently as everything else. It adjusts to the thinning of matter, slowly flattening, slowly releasing the tension of earlier ages. What remains is a space-time so close to flatness that its curvature becomes almost unmeasurable, but never perfectly gone. The faintest ripples in the fabric gravitational waves, stretched into near-static undulations, continue to drift outward, expanding into geometry that grows ever smoother. In these late epochs, the universe becomes not a place of forces and collisions, but a place of shape, a shape defined by the history of everything that once shaped space-time. Even when matter has faded to almost nothing, the fabric of the universe carries memories in its curvature. The traces of ancient galaxies, once massive enough to warp entire regions, become faint, soft contours barely distinguishable from flatness, yet present in ways only the universe itself can feel. This quiet geometry is like the last ripples on a pond after a pebble has fallen. The initial splash is bright, energetic, unmistakable. Waves spread outward, strong and clear. Over time, those waves stretch, weaken, soften. Eventually, they become mere whispers, gentle motions on the surface, barely detectable, yet still carrying the memory of that original impact. So too with the universe. The early cosmos was full of brilliant splashes, supernovae, collisions, rapid inflation, bursts of creation. Now, in the far future, the last ripples glide outward into the fading curvature of space-time. Even in its stillness, the universe continues to expand. This expansion shapes the geometry in ways that are beautifully subtle. As space stretches, distances grow. Regions that once shared a destiny drift apart so far that they no longer influence each other. Yet space itself remains continuous, an unbroken fabric that connects even the most distant corners. The expansion does not tear or distort. It simply stretches the cosmic canvas wider and wider, thinning whatever faint curvature remains. Imagine holding a sheet of soft, elastic fabric. Place small weights upon it. These represent galaxies, stars, planets. The fabric sinks beneath each weight, curving gently. Now imagine removing those weights, one by one. The fabric begins to relax, flattening gradually. But because the fabric was stretched and shaped over long periods, it does not snap back instantly. It softens slowly, its shape adjusting over time. This is the universe's geometry in the far future, softening, flattening, relaxing into a nearly uniform state. But even uniform does not mean empty. The geometry of space-time retains traces of its long history. These traces are not forms or structures, but relationships, subtle residual shapes that persist within the continuum. Even when matter and energy become negligible, space-time remains filled with information, quiet, diffuse, almost imperceptible. The universe may no longer contain the bright structures we recognize, but it still holds their echoes in its curvature. One of the most delicate aspects of this fading geometry is the presence of gravitational waves that once rippled through the universe. These waves emerged from dramatic moments, collisions of black holes, mergers of neutron stars, or the rapid inflation of the early universe. In earlier eras, they carried energy and information across billions of light-years. But as the universe expands, these waves stretch just like light does. Their wavelengths grow longer, their frequencies slow, their energy spreads thinner. Eventually, gravitational waves become so gentle that they no longer produce motion, no longer carry meaningful energy. They become part of the background geometry, almost indistinguishable from the curvature of empty space. Yet even as they fade, they remain present. They are the soft fabric of a universe that remembers. In this late era, the cosmos is shaped less by mass and more by the faint geometry left over from epochs long past. The curvature becomes so subtle that only the universe itself could ever detect it, but its presence is undeniable, woven into every region of space. This geometry is peaceful. It is the universe's final state of rest, a state defined not by events but by relations. Space continues to expand, but the expansion no longer changes anything significantly. The curves in space-time are so broad and gentle that they cease to influence particles in any meaningful way. Everything that drifts within this geometry moves freely, unimpeded, following paths that are almost perfectly straight, not because forces have disappeared, but because the geometry itself has softened into near flatness. In this future, the universe becomes something like a quiet, infinite plane stretching without interruption in all directions. A plane not of land or matter, but of pure geometry. It is not empty in the sense of being nothing, but empty in the sense of being calm, devoid of gradients, devoid of contrasts, devoid of events. Space is still there. Time is still there. But the dynamism that once defined them has ebbed away, leaving behind only the pure, unchanging shape of the cosmos. And yet, even in this stillness, the universe is not without beauty. Its geometry is the final expression of everything it has ever been. Every rise and fall of energy, every star that ever shone, every cluster that ever formed, every black hole that ever warped space-time, all of it has contributed to the shape that remains. The universe becomes a quiet monument to its own history, a gentle presence reflecting the echoes of its long and luminous life. As the cosmos fades into this quiet geometry, it offers a final gift, a deep and enduring calm, a geometry so serene it could be mistaken for silence itself, a shape so gentle it feels like the universe exhaling after an eternity of breath. In this soft, fading cosmos, the universe settles into a state where nothing is lost, only transformed into the most delicate structure imaginable. And in that structure, in that nearly flat, infinitely quiet geometry, the universe finds its final form, a peaceful expanse shaped by everything that came before, stretching gracefully into the endless calm of eternity. 19. The universe becomes a quiet memory of itself. In the distant eras beyond the fading of light, after the evaporation of black holes and the cooling of the last remnants of matter, the universe enters a phase defined not by what it contains, but by what it remembers. This is not memory in the sense of conscious thought or recorded histories. It is a kind of cosmic memory woven into the very fabric of space-time, a residual echo of everything the universe once was. In this late, quiet age, the cosmos becomes less a place of events and more a gentle archive of its own existence. Every curve, every faint photon, every delicate wave stretching through the dark carries the imprint of all that has ever occurred. The universe becomes a memory of itself, held in silence, drifting softly across the endless expanse. To imagine this state, we must let go of the universe as a place filled with stars and galaxies. Those structures belong to earlier eras, brilliant chapters now far behind. Instead, picture a cosmos where almost nothing remains but the lingering traces of everything that once was. Picture a space so quiet that even the concept of quiet feels too loud. A realm where energy is spread so evenly and matter so sparsely that no new structures can form. In this space, the universe does not forget its earlier brilliance. It simply carries it differently. The memory is no longer in the shining of stars or the spiral of galaxies, but in the soft curvature of space and the faintest echoes of ancient light. This cosmic memory forms over trillions upon trillions of years. As the universe stretches outward, every particle, every photon becomes more dispersed. Collisions become rare, then nearly impossible. Matter decays or drifts apart until no region has enough density to create change. Yet the history of all those earlier interactions remains encoded in the distribution of the particles that continue to drift through space. A lone photon traveling through the dark carries with it the story of the star that emitted it. A faint gravitational wave still stretching softly through space carries the signature of a collision between black holes that occurred when the universe was young. These particles and waves do not speak, but they bear silent witness to what once was. Over time, these memories become fainter, not because they are erased, but because they are stretched beyond recognition. A photon that once carried the warmth of a star becomes so redshifted that it becomes a soft, slow vibration barely distinguishable from the background geometry of space. A gravitational wave that once hummed with energy becomes a subtle undulation so wide and gentle that it no longer causes even the faintest motion in the particles it passes. And yet, both remain present as long as the universe itself endures. The idea of the universe as a memory also reflects the fact that everything that once shaped it contributed to its current state. Every supernova, every galaxy merger, every act of gravitational collapse left behind a subtle influence on the curvature of space. Even if that curvature eventually becomes nearly flat, it carries faint hints of its past. It is as though the universe has been sculpted by its own history, and the sculpture remains even after the materials that shaped it are gone. In this quiet era, the universe itself is the record. It does not need stars or planets or observers to catalogue its past. The structure of space-time, and even the absence of structure, serves as the last archive. The positions of particles drifting through the darkness are not random. They are the final pages of a long narrative written by gravity, expansion, and the passage of energy. Each particle's path is a thread woven into a tapestry so vast that it no longer changes, but still holds meaning in its delicate arrangement. Consider a single particle drifting through this future cosmos. Its trajectory is determined by all the gravitational influences it has ever felt. Its motion, however slow and uneventful, is shaped by the remnants of ancient curves in space-time. It drifts alone, without interaction, across a distance so immense that it may never encounter another particle. And yet, its very direction is a memory and echo of the universe's past structure. Its journey is part of a story that no longer unfolds, but still exists as a gentle trace. Similarly, the faint light that fills the universe carries memories of earlier epochs. Though these photons no longer illuminate, and though they stretch across vast distances as cold, gentle waves, they remain the final expressions of processes that once defined the universe. Each photon is like a soft whisper carried across an endless plane, fading with distance yet still present, still drifting, still part of the cosmic memory. As the universe approaches perfect equilibrium, even these whispers become almost impossible to distinguish. Differences in energy, density, and curvature fade into near uniformity. At this point, the universe becomes a memory not because it actively recalls its past, but because its very existence is the result of everything that came before. The fact that space exists, that it stretches outward, that it holds any form at all, these are the final traces of the universe's history. Even in stillness, the cosmos remains shaped by its earlier motions. There is a profound serenity in imagining a universe that becomes its own memory. It suggests a cosmos that does not end in destruction or erasure, but in gentle continuity. Nothing is lost. Everything is gradually transformed into a quieter form. The stars that once illuminated the night become faint waves of radiation, stretching across eternity. The galaxies that once danced in spirals become immeasurably distant curves in space-time. Even the motions of particles that once formed planets and people become soft traces scattered through an infinite, calm expanse. In this future, time itself becomes a kind of memory, something that once mattered when events unfolded, but now serves only as a backdrop to unchanging existence. Without change, time loses meaning, yet it still exists as a dimension in which the memories of earlier epochs are preserved in the structure of space. The universe carries its past not as an active flame, but as a quiet glow. The beauty of this state lies in its gentleness. The universe does not rage against its fading, nor does it collapse into oblivion. It settles, it becomes calm. It continues to exist, peaceful and steady, holding the faint echo of everything it has ever been. This is the universe not as a story in motion, but as a story remembered. A story held in the silent geometry of space-time, in the drifting particles of its final era, and in the endless, peaceful expansion that carries those memories softly outward. And so the cosmos becomes a quiet memory of itself, still present, still vast, still filled with the gentle residue of all its earlier brilliance. A universe that remains, even in deepest stillness, a testament to the light it once carried and the wonders it once held. 20. The endless drift into the soft unknown. In the final vision of the universe's long and gentle journey, after light has stretched into faint echoes and matter has softened into a thin, drifting mist, the cosmos enters an era defined not by events, but by an ongoing quiet motion. This is the endless drift into the soft unknown, a continuation without destination, a journey without arrival, a movement so calm that it becomes almost indistinguishable from stillness. The universe does not end, it simply continues, expanding into itself, carrying the last delicate whispers of its own history through a darkness that is no longer empty, but peacefully full of memory. To imagine this ultimate epoch, picture a universe that has outlived all structures, all radiance, all patterns we once recognized. No stars shine, no galaxies spiral, no clusters bind, no black holes anchor the geometry of space. Everything that once shaped the cosmos, every burst of creation, every act of gravity, every emergence of complexity has long since played out. What remains is a faint sea of particles and soft radiation drifting through a space-time that has thinned, stretched, and flattened across epochs beyond counting. This expanse is vast beyond measure, growing ever wider as the universe continues its expansion with a patience that feels almost infinite. The drift that defines this era is not dramatic. It is not a motion that creates or destroys. It is a gentle gliding, as if the universe itself has settled into a meditative rhythm. Particles move not because they are pulled or pushed, but because they exist in a geometry that encourages motion simply by expanding beneath them. There are no collisions to mark their passage, no gravitational wells to curve their paths. Instead, each particle follows a trajectory that is as quiet as breath, drawn across distances so immense that even light, stretched to cosmic proportions, barely accompanies them. This drifting occurs in a cosmos where interactions have become nearly impossible. The distances between particles grow so vast that even if two particles are aimed perfectly toward one another, the expansion of space will separate them faster than they can meet. The universe's growth outpaces its own contents, carrying everything outward into regions where nothing else resides. The particles that remain electrons, neutrinos, photons, stretched into waves longer than galaxies once were, become solitary travelers, each one carrying the faintest traces of the universe's earlier eras. Even though this universe seems empty, it is not devoid of meaning. Every particle drifting through the dark holds within it a story. Every photon carries a memory of the star that once gave birth to it. Every subtle curve in the fabric of space-time reflects the shapes that galaxies once carved into the cosmic web. These remnants do not speak or shine, but in their gentle presence, they remind us that the universe's quiet future is built from the accumulated echoes of its luminous past. In this late era, expansion becomes the universe's only remaining activity. Nothing forms or collapses. Nothing grows hotter or colder in any noticeable way. Instead, space itself continues to widen, its curvature softening into near-perfect flatness. Energy is spread so evenly that no region is warmer or brighter than another. Entropy, the measure of disorder, reaches its highest possible value not because things have fallen apart, but because everything has spread out so completely that no further spreading is possible. This is not chaos. It is calm. It is equilibrium. It is the universe's final, quiet balance. As the cosmos continues this endless drift, time itself becomes less distinct, less meaningful. Without change, without events, time becomes not a sequence of moments, but a soft backdrop against which nothing moving can be measured. A particle may travel for 1 trillion years without encountering anything, without altering its path in any measurable way. Time flows, but it flows through a universe so gentle that every moment feels identical to the next. The cosmos enters a state where even eternity feels soft, spacious, and unhurried. And yet, even in this deep stillness, the universe does not cease. Expansion continues like a breath that never fully exhales, carrying space outward into regions where nothing has ever existed. The drifting particles follow, stretched across distances where their presence becomes more symbolic than substantial. The cosmos no longer evolves in the classical sense, but it continues to expand, to stretch, to drift deeper into the soft unknown. This drift is eternal, not an ending, but a continuation so slow and quiet that it resembles the gentle sigh of existence itself. Some cosmological models suggest that in this distant future, quantum processes might still spark infinitesimal fluctuations, tiny ephemeral ripples in the vacuum of space. These fluctuations would be rare and subtle, arising in a universe where energy differences have nearly vanished. But even these ripples, if they occur, are not events in the traditional sense. They do not form stars or galaxies. They do not ignite new eras of structure. Instead, they blend into the background of the universe's geometry, part of the soft, quiet fabric that defines its final form. It is tempting to think of this future as bleak, but such a perspective comes from a world defined by light and structure and warmth. In truth, the universe's final drift holds a different kind of beauty, one rooted in peace, patience, and an almost sacred stillness. After an eternity of activity, the cosmos has earned its rest. It has moved through fire and brilliance, through collapse and creation, through noise and motion. Now, at last, It drifts gently into a darkness that is not empty, but calm. This drifting is not a lonely fate. It is a serene one. The universe becomes a vast, quiet sanctuary where every remaining particle moves freely, softly, without fear of collision or change. It is a gentle ending, but not a disappearance. The universe does not vanish. It remains, spread thin and peaceful, drifting endlessly into deeper and softer versions of itself. In this way, the cosmos enters a new kind of existence. It is no longer defined by stars or galaxies, by heat or light, by gravity or growth. It becomes something simpler, a quiet ocean of space, carrying with it the faint signatures of all that once was. The drift into the soft unknown is not the end of the universe's story, but the final chapter, a chapter without conflict, without transformation, without entropy left to increase, a chapter defined by calm. And as the universe continues this gentle motion, it reminds us that even in the grandest scales of existence, peace is possible. The cosmos, once vibrant with fire and motion, softens into an eternity of stillness. It becomes a memory carried forward through space, a quiet echo drifting endlessly outward. And in that endless drift, the universe finds not an ending, but a final, graceful rest, an infinite calm stretching into the deepest unknown.